All right. So can everyone hear me? I hope I'm audible. And yep, good. So I'm Sidhant, and I'll just give a brief intro about myself. I've been doing comparative programming since last 4 to 5 years or something. And right now I'm in college in a university named as National University of Singapore. And yeah, I've been to IOI and ICPC World Finals before. So yeah. Um, Apart from that, yeah, in case anyone in between doesn't hear the audio clearly, they can just like write it on the chat or something if there's an audio issue from my end. And if you have any doubts, then also you can write them on the chat. Preferably, like, okay, it's just recommended to do the chat for everyone. Don't message me privately so that other people can also see your doubts. All right. So moving on. The agenda for today is breadth first search and Dijkstra because this is graph theory session. In the previous session, we did lowest common ancestor and like how to find it fast for like multiple queries. This time we are doing more like the graph algorithms. Uh, so we'll start off with breadth first search. I'll first show like a generic pseudocode that most people write to implement breadth first search. Then we'll discuss these three ideas like this, like basically. So in breadth first search, generally the hardness of the question doesn't come from the fact. I'll just enable my video. Yeah. So in breadth first search, the hardness of the question. Can you please? In breadth first search, the hardness of the question generally doesn't come from the fact that the algorithm itself is difficult. Generally, everyone like after reading through the algorithm once or twice or like giving it 2-3 hours good and like having some basic graph theory knowledge understands the algorithm. In comparative, most of the questions which are tricky for breadth first search are the questions where you don't see the graph inherently, or if you see the graph, then you don't realize that you have to do a breadth first search. If I give you a graph and I ask you to do a breadth first search, that's a relatively much simpler problem than a question where you're not able to see how the graph is constructed. By what I mean by that is that so in standard graph theory questions, you're generally given like n nodes, m edges, and there are edges between pair of nodes and everything. Those are like explicit graphs. Where the problem itself states that there is a graph. Some problems have an implicit graph structure, which means that the problem nowhere verbally says that you have to draw a graph, but to be able to do the question, you need to like somehow construct a graph from that question. I'll give you an example later on with this water jug problem, or we can even look at dig jump, which is a CodeChef problem, and like it was present in that contest on the I think in the graph theory contest. Anyways, so we first do say a basic implementation of breadth first search. I'll just show this so that everyone is on the same page that how we generally people do breadth first search. So let's say we have n number of nodes, m number of edges, and for each edge, I get into two endpoints u and v, and let's say it's a weighted graph. So it's a weighted bidirected graph. By what I mean by bidirected is that there is an edge from u to v, that is this way. Also, there is an edge from v to u. Let's say, okay, generally speaking, the number of nodes will be of the order 1e5 plus 5 in the worst case. And the number of edges will be something like 1e6 at most for most of the questions. And we have a vector pair int to represent this. So the idea is that adj5 is a vector of pairs where adj5 I dot first is a neighbor of 5 and adj5 I dot second is the weight to go to this neighbor. Okay, can you explain weighted bidirectional graph? Okay, so basically there are two kinds of graphs, right? The one is unidirectional graph. Is this audio problem prevalent for everyone, or is it only Sejal? Because like CodeChef just told you that you have to click on the join with computer audio message. Yeah. So unidirectional graphs are those graphs in which when you say there is an edge from U to V, you mean that an edge goes from U to V. That is something like this. Whereas in a bidirectional graph, when you say there is an edge from U to V, you mean U, V. Okay, basically you mean an edge goes from U to V and an edge goes from V to U also. Both the edge is bidirectional, that is, it's on both the sides. You can go from U to V and vice versa. You can also go from V to U. That means bidirectional. So I'm saying, let's assume that this graph is bidirectional. That's why I'm adding the edge twice, once for U and the other time for V. I'm hoping like people are familiar with how adjacency lists are generally created, where the idea is that you have a vector of array, an array of vectors, and like, okay, why am I using pair, Nishan? Good question. So I'm using a pair because I want to put the weight also of the edge. So here the idea is adj 5, basically adj I j dot first denotes jth neighbor of node I. And adj I j dot second denotes the cost of traveling till this neighbor. So basically, the second value of the pair is the like how much time does it take or what's the cost. That's why it's a weighted graph. Weighted means that all the edges are not of the same weight. Okay, can you explain the sixth line? I'm not sure what the sixth line is. Okay. Okay, so let's go through this slowly. I think people are not familiar with adjacency list that much. Okay, let's assume it was not a weighted graph. Then does everyone understand doing this? If it wasn't a weighted graph, so I'm saying this is a unweighted graph, okay, and this will be just a vector of ends. Now, obviously, instead of this, some people do write it like this, which is also okay. This also works if you want to do. Yeah, this also works. So learners just as this. This also works. I just personally prefer to do this. Both the things work because your outer dimension. Okay, what doesn't work is this thing. If you do this, this won't work. So this won't work because MLE, memory limit exceeded, because you have like 10 to the 10 elements, which is too big, like almost like I think over 1 GB or something. So this thing won't work, but this thing and the other thing, which was this thing, both are somewhat equivalent. I just prefer the first way more because I don't have to do vector.resize and vector.initialize or things like those. Yeah, but both of them don't consume that much memory. This one consumes order n plus number of edges memory. And this one consumes just order number of edges memory. You can think about why it's so, but like I'm not going to explain it, but you can observe that both the values are going to be small. So this is basically order n plus m memory. And this is going to be kind of just order m roughly, but like n is generally going to be smaller than m, so you don't care. Okay, so now do people get why we are writing vector int adjoint? Yeah, I'm going to go to the BFS approach, but I first need to create the graph and like just so that people know how the graph is constructed and so how I'm accessing the adjacency list. Purnima, what is first neighbor and second neighbor? I didn't use the term second neighbor anywhere. This is the pair. So, okay. When you put the W inside, the idea is that now each edge has a weight also. Let's say the edge is from 4 to 10 with weight 40. Then here I want to put, then what I want to do is basically add 4 dot pushback 10, 40. Do people understand this now? That I want to push in both the combined information. That is, I want to push in the neighbor and how much cost will it take to go to that neighbor. So that's why instead of an int here, we put a parent because we want to put both the things. Yeah, Aryan's definition is pretty clear. What should I do? I've been using line 6 approach. Don't use line 6 approach to him because that will get you a memory limit exceeded when n is say greater than 10,000 or something, like roughly 10 to the power 5. Then that thing won't work. You need to do this thing. You can just Google up on how adjacency lists work. So the above approach, this is more like a adjacency matrix approach where you have a 2D matrix. So some values will be 0. A lot of values will actually be 0. And this is adjacency list. This is generally more used and like adjacency list. And this is also say memory friendly. That is, you don't use a lot of memory. And this approach is pretty much the same as the previous one. But line 11 is also 2D array. Okay, you meant line 12 or line 9. I don't know. But either ways, this is not a 2D array. This is a vector. This is an array of vectors. The benefit that comes is that you won't say node 1 has only few neighbors. Node 1 has say only 10 neighbors. Then how much memory will you consume? In matrix form, you will still consume order in memory. But in list form, you will only consume order 10 memory because you only have 10 neighbors. So each node will only consume that much memory as to how many neighbors he has. In adjacency matrix, that's not the case. Even if you have very few members, you'll still consume in square space. Which is the best for graph implementation using vector or linked list array? Doubt from YouTube. Okay, generally vectors. Vectors are the way to go. Yeah. I mean, on a compiler level also, vectors are faster than linked lists. And if you want to, like, there is a very rare scenario where you actually have to delete stuff. So linked lists are beneficial only if you have to delete stuff from between, right? But in graph questions, that's generally not the case. You don't want to delete a lot of edges or something. And even if you want to, you can just put a -1 value or something and then skip it. Small recap on vector. Okay, the recap is basically that. So if you create a vector int v and you don't put in anything in it, then this consumes 0 memory, somewhat 0 memory. Whereas if you create a int vn, that's an array, this will use n memory, right, straight away. So if you do, let's say you're going to have very few neighbors. Let's say you're going to have 30 neighbors. Like node 1 has 30 neighbors. If his adjacency list is represented using an array, then the issue comes that you'll still consume n memory. But if his adjacency list is represented using a vector, then you'll only do a pushback 30 times. So you'll call pushback, but you'll call it 30 times. You won't call it more than 30 times. So you'll only consume 30 memory. You won't consume n memory. And in totality, you will consume m memory, which is where m is the number of edges. In this method, in the vector method. Yeah, vector is dynamic sized. Yeah, I was just explaining from the point of view of graph theory. Why is vector preferred over an array? Yeah, bottom line, adjacency matrix is quite useless. I think most people use adjacency matrix only when they want to do Floyd Warshall, because doing Floyd Warshall on an adjacency list is kind of dumb, because Floyd Warshall only works till like n equal 100 or something. So if you have n equal 300 or 400. So if you have n equal 300 or 400 and you want to do Floyd Warshall, which is a all pair shortest path algorithm, you can Google up what all pair shortest path means. Then you can generally do a matrix, because 300 square is not a lot of memory. Nishant, I don't think we are going to do a lot of questions. Maybe we'll cover one CodeChef question. We are going to go more through the techniques. So let's start. Okay, we have some Python doubts. I'm not going to clear that because we are not going to use Python. Weebly computationally slow. Why not a map of edge to vector of edges? Okay, I'm not sure what you mean by map, but I know if you try to replace anything here with an unordered map or a map, things will get slower. And you don't really need the properties of a map here. Sometimes people actually do need properties of set. So sometimes we do put set. Let's say you want to support deletes also. You might put unordered set of a set here if you want to support deletes, or you might put a linked list. But yeah, that's the case. But like most, and I think in generic, like in 95% of the graph questions you'll see, you won't have to use anything else. So moving on. Now, how does a BFS work generally? So you have a queue, right? And okay, I'll delete all this stuff. Shit. Yeah, you have a queue, and let's say our source is node 1. Then you do q.push source. Okay, and you have this thing. So this is like the generic structure of how queues work, like BFS works. You do a while queue is not empty, then you take the front of the queue, then you pop the front of the queue. I'm just showing the standard BFS implementation about it. Then you say iterate over the neighbors of u. So to iterate over the neighbors of u, you can use some syntax like this if you know C++. I think this is C++ 11 or C++ 14 feature, not sure which one, but like this is pretty neat feature, which is basically, so the idea is this: adjacency u is actually a pair, right? Okay, I mean, it's a vector of pairs. So I'm looping over that vector using this for auto syntax. And then I'm unwrapping that vector into two elements, v and w. So the first element of the vector is going to be denoted by v. The second element is going to be denoted by w. This is a very prevalent or old feature in Python. Like in Python, a lot of people used to do something like a comma b is equal to function call. So they used to get the first element of the function to a and the second to b. And this recently came to C++. Okay, not recently, more like 2014 or something. But yeah, sometimes people use it and sometimes they don't. Either way. Line 30 again, please. Okay, I mean, okay, I'll just explain that you access it by reference, not by copy. Yes, okay. So I'll just tell you guys what's the difference here. So the standard way to do this thing is generally like what I used to do before was I used to create this thing. And then I used to do v equal vv dot first, w equal vv dot second. Okay, this is one way to go about this. This basically, now does everyone understand this portion, like this portion, where I'm just looping over to that vector, trying to get my neighbor node and the neighbor's weight. And then obviously I haven't explained the BFS algorithm yet and we haven't gone through it, but that's one looping way. The other looping way is to do this, which is adding an ampersand. This is passed by reference, not passed by copy. You don't need to go into the technicality of most of these things because it's just a pair. But anyways, like you can do any of them. Nobody really cares, at least for this example. And if you want to understand this pass by reference, pass by copy thing, then just Google it up. It's basically a C++ thing, which is like either I'm doing a pass by value or I'm doing a pass by copy in functions. Let's say you call a function f with a vector. Now, if you inside the function definition, if the function is, let's say this void f vector int v, okay, and then it does something, blah, blah, blah. Then this is passed by copy. That means if vector v is of size 1000, that means when you're calling the function, you're creating a new copy of that vector. So it costs you 1000 steps. And then let's say you change something here. You say v5 equal 10, and then you return. The vector won't be changed. Like here, the vector will still remain unchanged because it's a pass by copy. You copied out the entire thing, and now the function doesn't know the original thing. So when the function changes, it changes its local copy. Whereas if you had done something like an ampersand here, that's passed by reference. So you're saying, don't copy the thing, just take a pointer of it. Okay. So moving on, we have this thing. Now, generally what you do is, so you got the neighbor and you got the weight. Okay. So one thing I messed up was BFS generally works on unweighted graphs only. I don't know why I made it weighted. So let's just remove that. Yeah. My bad. I'll just quickly change this. Breadth first search only works on unweighted graphs. Breadth first search doesn't work on weighted graphs. Dijkstra works on weighted graphs. That's why I'm removing that thing. Yeah, it was unnecessarily complicating it. Nishant, I don't like, you have to write full sentences, bro. I can't understand the way you're writing. Like, just ask the precise question. And if you want me to slow down, then tell me. But like, okay, so I'll just re-explain what has happened till now, which is that breadth first search doesn't require, like the breadth first search doesn't work on weighted graphs. I haven't even written the breadth first search. How can you understand it if it's not been written also till now? So yeah. So you also have a distance array in breadth first search. You have a distance array, okay, which is basically what's the distance of that node till source. So initially the source distance is 0, right? And then you say, okay, and you mem set the distance array to say -1. Okay. Now the idea is when you visit a node, you say if it hasn't been visited till now, that is if the d of v is equal -1, then we should visit it. And what should we set its distance to? We should set its distance to my distance plus 1, and we should push him inside. That's pretty much it. Yeah, that's BFS. Okay, I'll explain the logic, Saurabh. So the logic of breadth first search. Okay, does everyone know what breadth first search aims to do? I'll go to my iPad and just explain everyone what breadth first search is meant to do, and then we can move on from that. Also, in general, I feel like people are very less familiar with graphs compared to DP and greedy. I don't know what the reason for that is. Maybe like I feel one of the reasons can be that for graphs you have to explicitly read the theory sometimes. For greedy and DP, that's not the case. Even if you just keep on doing a lot of problems, you get a hang of how greedy and DP work. But for graph, you actually have to read the theory, like initially in the initial stage, just to know how the algorithm works. Because even like no matter how many questions you see, if you don't know how breadth first search work, you can't crack a breadth first search question. So, okay, let's say this is the graph. I'm going to label each node. Okay, I'll go a bit slow. So I'm just explaining what a breadth first search does. Okay, so what we want to do is from node 1, we want to find the distance till every other node, the shortest distance. Example, from node 1, the shortest distance to node 2 is 1 unit away. So every edge is 1 weight. That's why I said it's an unweighted graph. That means every edge is of the same weight. We don't care about the weights. So what's the distance to node 2? That's 1. What's the distance to node 5? Now that is not 1, 2, 3, 4. That's the, like I'm asking the shortest distance. So the shortest distance is 2. What's the distance to node 6? 3. What's the distance to node 4? 2. What's the distance to node 3? 1. What's the distance to itself? 0. So all these values are basically what we want to generally find in a breadth first search shortest path algorithm. Okay, so in a breadth first search, what we aim to do is try to find the shortest path, right? And the difference between breadth first search and depth first search comes from the fact that breadth first search is generally targeted, like generally used when you want to find shortest paths, like something of the sense, like I want to go to that node as fast as possible. Whereas depth first search is just used to explore the entire graph. If you just want to explore the graph, you don't care about the order in which you explore, and you don't care about finding out the correct distances, then you can use a depth first search. But if you do care about those things, then you generally use breadth first search. Obviously, breadth first search only works on unweighted graphs. So generally, like a key thing to remember is for unweighted graphs, you use breadth first search, and for weighted graphs, you use Dijkstra. Obviously, this is under the assumption that you're trying to do something like shortest paths. Like the question involves something along the lines of trying to find shortest paths or closest nodes or nearest distances, minimizing the distance constraint. Only then you think about these two algorithms. And in the unweighted scenario, you generally think about breadth first search. In the weighted scenario, you think about Dijkstra. Now, does everyone get the motivation of why we are doing a breadth first search? So that we are able to find these values correctly. That is, how close is node 2 with respect to node 1? How close is node 5 with respect to node 1? How close is any other node with respect to node 1? Okay, that's the motivation. So the idea is you start from node 1. So let's say I start from node 1. I put node 1 in a queue. So let's say I have a queue and I put the node 1 in a queue. Now I take the queue's front, which is node 1. I pop him out and I say, explore every neighbor of his. So 2 is a neighbor of his, 3 is a neighbor of his. So add those guys in the queue with distance 1. Okay, why distance 1? Because when 2 was being added, it was being added by node 1 and the distance of node 1 was 0. And the distance of node 1 was 0. So 0 plus 1 is equal to 1. I'll explain this more further. Now when 2 and 3 are added, say the queue's front is 2 now. You'll pop out 2 and you'll see 2's neighbor. Now 2's neighbor are 1, 4 and 5. 1 is already visited, so we don't care about it. 4 is not visited. So we say 4's shortest distance is the shortest distance to come till node 2 plus 1. That is the shortest distance to node 4 is 2. So we calculated this value and we pushed in 4 inside our queue. Similarly, we saw 5 also. We are seeing every neighbor of 2. So we saw 1, we saw 4. Now we are seeing 5. 5 is also unexplored. So we'll explore it. And what's the shortest distance to 5 now? It is this 1 plus 1, because the shortest distance to come to node 2 was 1. And we added another 1 to pass through this edge. So 2. And we push in 5 also in the queue. Now every neighbor of 2 is explored. So he's popped. We move on to the next guy in the queue, who's 3. So now we say explore every neighbor of 3. So we say, how many neighbors does 3 have? He has neighbor 1 and neighbor 4. Now he sees neighbor 1, but he says that he's already explored, so I can't explore him. He sees neighbor 4. He cannot explore neighbor 4 also. Because neighbor 4 has already been pushed in the queue. That's why he can't explore him. Is this clear? Why node 3 can't explore node 4? Like why node 3 won't unlock node 4? Because node 4 is already in the queue. So he already has his correct distance. So node 3 doesn't have anyone to explore actually. So node 3 will just pop out. Then you come to node 4. Even node 4 doesn't have anyone. Say maybe there was another node and edge, say node 7 this way. Then node 4 will have someone. So then node 4 will have 3 neighbors, node 2, node 3, node 7. He can't explore node 2 because he's already explored. He can't explore node 3 because he's already explored, but he can explore node 7. So he'll push in node 7. And what's the weight that he's going to set for node 7? He's going to say, take my weight plus 1. So that's 2 plus 1, 3. Now node 4 is popped. And you go to the next guy, which is 5 in the queue. So I'm every time notice that I'm going to left to right order in the queue, which is basically taking front again and again. I'm popping also from the front and I'm taking the front to access and I'm pushing in from behind. That's the structure of a queue, right? I'm pushing in from behind and I'm popping from the front. So when you see node 5, you see how many neighbors does this guy have? Node 2 and node 6. Node 2 can't be explored because he's already explored. Node 6 can be explored because he's unexplored. And what will be the minimum weight for node 6? It will be my weight plus 1. So node 5's weight is 2 and plus 1. So 2 plus 1, 3. And then I'll push in 6 also because he's explored now. And I'll pop out 5. Now 7 and 6 won't explore anything because their neighbors have already been explored. So they'll just pop out. And after this, the red values that you see, these values that you see are basically the distances. Does everyone get the broad idea of how the algorithm works? You have a queue, you come on each node, you try to explore its neighbors, and you only go through those guys which are unexplored, and you update their distances. And you push them in the queue also. Okay, won't that implementation run into an infinite loop? No, that implementation doesn't run into an infinite loop because I only push one node once in the queue. I don't push a node more than once in the queue. I make sure of that. Right? Notice here we only push one node once in the queue every time. Because when we were at node 4 and we saw, okay, we have node neighbor 2, neighbor 3, neighbor 7, we didn't go to neighbor 2. So we didn't push neighbor 2 again because he was already visited. So yeah, so Hem, you're correct. You need a visited array. Instead of a visited array, you can also work with the distance array. So if you set the distance array to -1 initially for everyone, okay, and then later on you try to correct these values. So let's say this guy gets node 0 value, this guy gets value 3, this guy gets distance values 2, this guy gets value 1. Now when you're at this guy and say you have an edge to this guy, you know he's already visited because his distance doesn't say -1. Had his distance said -1, you would have known he's unvisited. So either way works. You can have a visited array also. If you don't want to keep the visited array, you can just put that visited information in the distance array. And the way I put it in the distance array is that I initialize the entire distance array with -1s. And then I say, if the guy's distance is -1, that means he's unvisited. And if it's not -1, that is anything else, then he's visited. Okay, fair enough. Yeah. So in this graph, the visited order, yeah, okay. So this was the actual implementation. The way people think about algorithmically about BFS is what Aryan just mentioned, that you, yeah, I'll paste the -1 trick. The way that people actually think about breadth first search and algorithmic senses, they try to think about it like a heighted thing, which a lot of people mentioned, like levels wise. So when you are at node 1, you explode node 1, then think about what did you do. You first went to node 2 and then node 3. So you got node 2, node 3, right? From node 2, what all did you explore? You explored node 4 and node 5, right? And from node 3, what did you explore? Nothing. You didn't explore anything because both these guys were already explored. Now from node 4, what did you explore? Node 7. From node 5, what did you explore? Node 6. And from node 7, what did you explore? Nothing. Node 6, what did you explore? Nothing. So this is like known as the BFS tree. A lot of people call it the BFS tree, which is basically saying in the order of which I explored, like node 1 was the guy who explored node 2 and node 3. Node 2 was the guy who explored node 4 and node 5. Node 4 was the guy who explored node 7, and node 5 was the guy who explored node 6. So this becomes a tree, and it's kind of like the shortest path tree in some sense. Like if you want to know the shortest distance from node 1 to node 5, it's 2. From the root, all these guys are like at their shortest heights possible. So this is like when people talk about the height thing in a BFS, this is height 0, this is height 1, this is height 2, this is height 3. What we mean by heights here is that if a certain node is at a height x, that means he's x distance away from node 1, the root basically. No, this is not a minimum spanning tree. Don't confuse it with the minimum spanning tree. It is a tree, but it's a breadth first search tree. Mihir, can we neglect the exploration of visited nodes here? Okay, you always have to keep in mind that you cannot by mistake explore a visited node again, otherwise you will run into an infinite loop and your program won't terminate. So you have to always keep track that, oh, I shouldn't visit a visited node again. Because, okay, breadth first search works on graphs which can have cycles. Breadth first, this graph can have cycles. The tree form doesn't have cycles, but this graph can have cycles. So you have to always make sure that you don't run into infinite loops. So you don't run into accessing visited nodes again and again. Gagandeep. If it is visited and if we can find the shortest distance for that node in some path, means that the current distance is less than this distance. Do we handle that scenario? No, Gagandeep. That's the property of breadth first search. If that node is already visited, you have explored it, then you are guaranteed that you have already found the correct shortest path to that node. You have already found the correct shortest path to that node, so you don't have to update him again. And that's because the graph is unweighted. Had the graph not been unweighted, let's say some edges were of weight 2 and some edges were of weight 3 or something, then that property breaks. So that's why you need the unweightedness. But good question. There is nothing like a root node in BFS. Anshul, from the node that you start the BFS, I define that node as the root node. You have to start the BFS from some node. You can't start a BFS on the generic graph. Like there has to be a node from which the BFS starts. And that's generally considered to be the root node for that BFS. So Subhajit, it depends what you're trying to find. If you're trying to find the shortest distance of nodes with respect to node 1, then your root node should be node 1. If you're trying to find the shortest distances with respect to node 2, let's say with respect to node 2, node 3 is at a distance 2, right? Then you need to start a BFS from node 2 and not from node 1. If you start from node 1, then you're getting an incorrect answer. Yeah, like, let me think. Yeah, as an example, okay, I don't have an example straight away, but yeah, you should be careful of which node you start the BFS from. I mean, depends on the objective. So we have this. Now let's switch back to the implementation. Sorry. So yeah, and if you want me to re-explain anything, just let me know. I'm going through it slightly faster, maybe, I don't know. So we had created the adjacency list, right? Now we said what I was explaining, that we set the distance array to -1. Alternatively, if you want to see something simpler, I can show you the visited array method. So you have a visited array method, visited array, and you set everything in the visited array to false. Okay. By default, also it's false because it's a global array. But anyways, we create the queue. We set the distance for the source to be 0. We mark the source as visited. Okay. Here we say if visited v equals 0, that means if v is unvisited, then this line is pretty straightforward. Distance of v is equal to distance of u plus 1, and we push in v. Also, we mark v as visited. That now it's visited. So basically, vis0 denotes that it's not visited. So what all doubts do people have here? Gagandeep, good question. Either while polling or pushing the node in the queue, what would be the better approach? I'll explain this question like in detail because that's a very common bug that people make. Okay, Pranav, I'll slow down a bit. Why do we do 37? Okay. I think people don't understand the concept of D array. So dx should denote the shortest path weight from the shortest distance, you can say, from node 1 to node x. That's what dx should denote. Now do people get it? So that's why d of source is 0 itself. Okay, from node 1, like from source to node x, you can use source word. I'm just setting source to 1. So that's why this distance is 0, because it's a default node, right? And then his visited is 0. Okay, let's say the graph is 1 to 2, 1 to 3, 2 to 4, 3 to 4. Let's say the graph looks something like this. Now what we'll do is we'll push in queue in the queue 1. So how will the queue look? The queue will look 1, right? That's it. Now we'll access the queue, we'll pop the front guy. So now how will the queue look? It'll look empty. Now we'll access every neighbor of u, and what is u? U is 1. Why? Because you accessed the front. So what value of u did you get? You got 1 here. Sorry, you got 1 here, and now q was empty. Here you accessed every neighbor of u. So v will be what all values? V will be 2 and v will be 3. When v is 2, he is unvisited. So you will go through here and you'll set d of 3 equal d of 1 plus 1, which is equal to 1. Because notice above what I did, I set d of 1 to 0. And also I'll mark him visited. So I'll mark vis3 1 and I'll push him. So now q looks like earlier it was empty. I pushed this guy in, so it was, now it's 3. Now in the next iteration, v comes out to be 3, right? Now v is 3 in the next iteration because 1 has 2 neighbors, 2 and 3. Again, what happens in visited? Visited 2 is false. So you say d2 is equal to, again, d1 plus 1, which is 1. You mark him visited. So vis2 is 1. And you push him in the queue. So this queue becomes this 3, 2. Now you go inside again. And this time you see U is Q dot front. So what is U? Instead of 1, it's going to be 3. The Q looks like this, 3, 2, and so on. So basically every time we take the front of the Q, okay, line 26 is just equivalent to this line. Both of these lines are same. Line 26, line 27, both of them are same. It just sets everything to 0 in the entire array. Okay. And what other questions do we have? If we mark the visitor during popping, we need to print the source before and right. Is fine with me, but I think students will want to pause it every RA assignment to really understand it. Abhishek, you're correct, but I think it's like, do people want to have a dry run of this algorithm? I mean, having a dry run of this algorithm is actually, I don't know. I'm not sure if that can actually help people, because I think visually seeing it helps a lot rather than seeing it through the code simulating. To get the idea, what we're doing is we are taking the front every time. And when we take the front, then we pop him out. So we cross him out, what we did on the iPad. And after that, we loop over his neighbors. If the neighbor is unvisited, that's why we have this if condition. Then we set his distance correctly, which is the previous guy's distance plus 1. We mark him visited and we push him. We do these 3 things. We set his distance correctly, we mark him visited, and we push him. And then we check the next neighbor. So let's say the next neighbor is visited. Then we don't do anything for him because this condition is not run. So we just skip him and so on. Okay. So, okay. One interesting question that came up by Gagandeep was this thing, which was pretty cool. What happens if you don't set visited here? Okay, but instead set visited here. So it's a good exercise to actually understand what's happened in the algorithm. What is the difference in the 2 approaches? We setting visited here versus setting visited here. So now line 37 is there, but line 42 is not there. The alternate is that line 37 is commented and line 42 is not commented. Okay, one of them is wrong actually. So this one is actually not per se wrong. Okay, let's say I remove this. Yeah, I remove this visited source equal 1, because if visited source equal 1, okay, I can even keep it actually, nobody cares. Yeah, but yes, Shruti is correct. So the thing is, this one is wrong. Like marking visited here is not per se wrong, but slower, much slower, exponentially slower. Okay, and this is a very common bug that people make. And if the problem setter is smart, then he'll have a case that actually makes you TLE with this implementation. Because what happens here is that the visited is set when you process the node. So I can give you an example. Let's say the graphs look like this. Let me think about the graph for a minute. Yeah, let's say the graph looks like this. So one has an edge to 2, one has an edge to 3, one has an edge to 4, one has an edge to 5, dot, 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 one has an edge to n minus 1. Also, 2 has an edge to n, 3 has an edge to n, 4 has an edge to n, dot, 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 n minus 1 has an edge to n. Does everyone get how this graph looks? So everything, like 1 is the source. From 1, everything is going out, like 2, 3, 4, 5, dot, dot, dot. And then from every of these guys, it's going to n. 2 goes to n, 3 goes to n, 4 goes to n, dot, dot, dot. Right? So it's a big diamond kind of structure. Now, if we have this graph, what will happen if we do this? Observe carefully. We'll mark the node visited 1. We'll mark the node 1 visited. So, and then we'll push every neighbor of his into the queue. So how will the queue look? The queue will look like 2, 3, 4, dot, 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 n minus 1. Right? When we, so everyone understands the graph structure, right? Node 1 is at the source, node n is at the destination, and in between you have node 2, node 3, node 4, dot, 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 and every pair is connected like this. Like every node is connected with node 1 and every node is connected with node n. And you have a lot of nodes here. Right? Now, when you process node 1, your queue will become full, because think about this. Initially your queue is empty. After the loop, how will your queue look? You'll push in every guy. You'll push in 2, you'll push in 3, you'll push in 4, dot, 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 n minus 1. So you'll push in pretty much every guy. Now, for each of those guys, so this is how your queue looks, right? Now, for each of those guys, you'll see their front. You'll mark them visited. That's okay. You'll go here. You'll see that node n is unvisited. When v sets to be n, you'll notice he's unvisited. You'll push node n. So in the first iteration, what will it look like? 2 is popped out. So you have 3, 4, dot, 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 n minus 1, and also n, right? N will be pushed, right? Because when node 2 is processed, he has 2 neighbors, node 1 and node n. Node 1 is visited, so you don't care. Node n is not visited, so you'll mark him. Okay, you'll set his value correctly and you'll push him in, right? But still, visited of node is 0 right now. This is, be careful here. Like, the visited of node n is 0. We never set it to 1 till now, right? And that's how the queue looks: 3, 4, 5, dot, 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 till n. Now, in the next iteration, you'll come here. So how does the queue looks? It looks like 3, 4, dot, 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 n, right? Now your queue will be 3. You'll mark him visited. You'll pop him. So how will your queue look? 4, dot, 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 n minus 1, n. And then again, you'll see neighbors of 4. So one of them is 1, the other one is n. Node 1 won't be accessed because visited of 1 is 1. So you will skip this. But visited of n is still 0. So you won't skip this. You'll actually go through this if condition. You'll set his value again, which doesn't matter. You'll set it correctly. You don't care about that detail. But you'll push him again also. So now your queue looks like this, and 2 times n. And you keep on doing this, and eventually your queue will look something like n, dot, 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 n, which is like n times n. And each of them is going to be processed through this thing. So had node n also got a lot of neighbors, let's say node n had a neighbor n plus 1, node n had a neighbor n plus 2, node n had a neighbor n plus 3, okay, dot, 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 and node n had a neighbor 2n. Then think about what will happen here once the queue becomes so big with n's. Each guy will go through this loop. They'll go through their adjacency list, which will cost how much time? Order n time, right? Because they have n neighbors, n plus 1, n plus 2, up till 2n. And that's why this will become slow, because this guy is pushed in multiple times and he has a lot of neighbors. The intuition is that nobody should be pushed more than once in the queue, because if they have a lot of neighbors, it's kind of like if this guy has a lot of neighbors, then each of that neighbor is going to be accessed so many times. So it becomes n square. N is pushed n times in the queue, and each time he is going to process his n neighbors. So how many total neighbors is he going to process in total? N square, right? So your algorithm just got like time limit exceeded. So that's why this is a very important detail, and it's very easy to miss. Yeah, queue will be flooded with duplicates. So insertion, everything is large. Yeah. Good question, Karthike. It will be an integer. AutoV, when you do AutoV, this is an integer. This is not a pointer. Even if you do this thing, it's still an integer. It's just a reference. So if you do this and you say v equal 5, that means you're actually changing the thing inside the adjacency list. But if you do this and you say v equal 5, that means you're not changing the thing in the adjacency list. Like the adjacency list still preserves. It doesn't get like that value 5 if you don't put the ampersand. But if you put the ampersand, then the value actually gets changed. But anyways, that doesn't matter in this question per se. So does everyone understand the implementation of breadth first search? Hetal, I just explained, so I can just tell you, if you do it the wrong way, then your complexity will be n square. That means if you do it like this, where you mark it visited here, and you don't mark it visited here. The important thing is that at line 40, it should be marked visited. If you do both the things together, nobody cares. If you do both the things together, it is still V plus E. It is still fast. Okay. But if you remove this line 40, then things get messed up. Then you go slow. Then you go order V square. So basically this line 40 is important. Like this line should definitely be there. Whatever line 41. What's the complexity here? V plus E. Because number of things that you push in the queue is how many? V, right? So this outer while loop is going to run V times. And each time you have a different node and you're accessing that node's neighbor list. So how many total times is this line 36 run? Order E times. Because E is the total number of edges. So each node has some neighbors. And if you add up all those neighbors, then you'll get 2 times the number of edges. So that's 2E. So it's like the number of operations are actually roughly V plus 2E, which converts to order V plus E in complexity analysis. Do people understand this now? But V plus E is equal to V square. No. Say my V is 10 to the power 4. Okay. And my E is 3 into 10 to the power 4. Then my fast breadth first search, this method, the thing that we wrote just now, I mean, it's a standard breadth first search. This thing is actually 4 into 10 to the power 4. It is not 10 to the power 6. Right? E can be V squared sometimes. Yes, E can be V squared sometimes. But if a question has V equal 10 to the power 5, and it is a comparative programming question, that means it's on CodeChef or Codeforces or some online judge, then nobody will give you E equal 10 to the power 10. Because think about this. How will you input so many numbers? You'll run out of time before you just input all these edges. You'll have to take in 10 to the power 10 integers, which is very slow. So if V is 10 to the power 5, most of the cases you're going to get E something like less than 3 into 10 to the power 6 for majority of the problems. You're correct that edges can be indeed V square, but if your V is pretty big, then E won't be given to you in the order V square because you can't take in that much input. If you were trying to take in the input of the size 10 to the power 10, then you'll just run out of time. Like, yeah. Because think about this, you can almost do 10 to the power 7 or 10 to the power 8 operations in 1 second. So you won't be able to do these many operations in 1 second. So in programming interview, both are equivalent. Not really. I mean, okay. So the thing is, you always say that E is less than equal V square. Okay. But the algorithm's complexity is always defined like V plus E or V square. You can't just substitute E with V square everywhere. Yeah, you can't do that substitution. What editor is that allows fancy less than equal operator? Okay, the editor is normal Vim. The font is Fira code. You can just Google it up and like install it on your terminal or something, and like that font basically gives you this thing. Yeah, it still copy paste as normal less than equal. It's not a different Unicode character or a different ASCII character. It just looks different. I'll go through the plugins thing in a while. Yeah, I mean, someone asked me for the VimRC also, so I'll check. Anyways, we have this, right? So everyone understands breadth first search, the standard breadth first search. Okay, let's go through the agenda again. Okay, so we understood the least number of steps idea, right? That we have to find the shortest thing. And okay, let's go through this water jug problem via iPad. Okay, another thing we just now discussed that we are doing order V plus E. So just think about this. For most questions, your V plus E in totality, which is basically number of states plus number of transitions in totality, will be something like 10 to the power less than equal to 10 to the power 6 or maybe 10 to the power 8, but something around this. Like if it's bigger than that, then breadth first search won't work. Just keep that in mind. Okay, now let's go through water jug problem, because that problem will show you how breadth first search is hidden in graph problems. Sure, Naren. How 2E can you explain? I don't get what you mean by 2e. V plus 2e, okay. Okay, basically 2e was by like how many edges are you exploring? So let's say you have a graph, okay, and each node has some neighbors, and you're adding up those neighbors, like the sizes of those neighbors. Example, in this question, if I get tot equals 0, some variable, and I do this, okay. Yes, the water jet problem is not there on CodeChef DSA series, but I mean, it's a pretty good problem. So we should go through it. Let's say we are going to do this tot plus equal add I dot size. Okay. Now, can anyone tell me what's the value of tot going to be in terms of V and E? And let's say this is like not N, this is V. Yeah. The question is, what's the value of tot going to be? 2E, correct. So now do people understand why I was saying 2E below here? Because that's how many times you're going to go through that loop. If it's still unclear, I can explain the broad idea that so when you're doing this tot plus equal add joy dot size, what you're doing is you're counting all the edges from that node, right? So what you're doing is you're fixing a node, counting all the edges around that node, and then doing it for another node and so on. So each edge is counted twice. Let's say there's an edge from node A to node B. When your loop hits node A, you're going to count that edge and you're going to go around. And when your loop hits node B, you're also going to count that edge again and go through. So each edge is counted twice. So that's why this is 2e. And that's how you get the thing. Like here, that I explained. That this thing actually runs 2e times. So that's why the complexity is v plus 2e. Since it's a bidirectional graph, so each edge is counted twice, right? Yes, you can say that. Yeah. I mean, we don't go through the details. I mean, this can be 2e, 4e, nobody cares, honestly. I'm not sure of bidirectional case. I actually didn't think about it, but like, yeah, but that's not the constraint. The idea is that it's going to be constant times e, some constant, and the constant is going to be small, like 4, 5, 8 at most. So that's why the complexity is going to be v plus e. And yeah, so that's pretty much it. And like, let's try to go through the breadth first search water jet problem. So I'll first explain the problem. You might have seen this problem in a lot of, I don't know, a lot of like, it's common, I feel, maybe not interview per se, but like something of that sort. Give me a moment. I'm trying to figure out how to connect. Okay, so it's connecting. Share screen. Okay. Yep, I think it's connecting. All right, so we are doing water jug problem. So in the water jug problem, what's the problem generally? The problem is something like this. You're given some jugs. Let's say we are given 3 jugs. Okay. And let's say one of them is of capacity 10 liters. The other one is of capacity 7 liters. The other one is of capacity, I don't know. Okay, then let's make this small. Let's make this 4 liters and this one 7 liters. Okay. Now you have a tap here, some global tap, which can give you water. Now, what you can do is basically you can ask the tap to fill in any one of your jugs, right? So, and in the water jug problem, either you fill the jug completely or you don't fill the jug. You can't half fill the jug or like 1/4 fill the jug or something like that. You have to fill the jug completely. Okay. So let's say you fill the 10 liter jug completely. Okay. With water. Now, what you can do is you can do operations like shifting water from one jug to another. So one type of operation is filling a jug from tap. Tap is like an infinite source of water. The tap gives you infinite water. You can ask it anytime and you can waste as much as you want. Nobody cares in this problem. And once you fill the 10 liter jug, you can maybe pour it into the 7 liter one. So this is pour operation. In the pour operation, what you do is you take two jugs, that is A and B, and you transfer water from A to B. Okay. So in this, how will the transfer work? This is a 10-liter jug and you're transferring it to a smaller jug of 7-liter. Okay, let's make it look smaller also actually. This looks pretty big right now. Right? Yeah, it's slightly smaller. And then what happens? This jug gets filled completely. Obviously, this jug like gets partially filled. And how much will be left in this jug? 3 liters, right? So the idea is this goes till like roughly 3-liter mark, right? The idea is that when you fill in from one jug to another, you can only fill till the time the spill doesn't happen. So you can't overspill. You can't waste the 3 liters. The 3 liters will stay here. Okay. Now you can even pour in this 3 liters to the 4-liter one if you want to. You can keep on doing this stuff. Does everyone understand what all operations do we have here? Roughly, like we can again fill in from tap this 3-liter jug and make it full, like make it again back to 7 liters. So you have multiple operations. One is take the tap and fill one of the jugs completely. The other is take 2 jugs and transfer water from one jug to the other one. And by transfer, I mean keep on transferring till the time either this jug becomes empty or the other jug becomes full, and stop that. I stop at that time. The third one is empty a jug. So you also have this operation empty a jug, which is basically saying just throw that water. So you can say I don't want this 7-liter actually, I just want to throw it. So I just throw it out in the drain and then I have 0 here again. Okay. Yeah, it's a common problem. You will find out on Geeks for Geeks or you'll find it on the CodeChef one. I'm not sure which version of the problem they're talking about, but it's a pretty common problem. So sometimes the question is how many, like what all different quantities of water can you end up with? We are not tackling that question really. What we are tackling with the question is minimum number of steps needed to obtain, let's see, say 2 liters in any one of the jugs. Okay, let's say this is the question. So you're starting off with 3 empty jugs of size 10-liter, 4-liter, 7-liter. And your aim is to do some steps and reach some scenario like this 10-liter, 4-liter, 7-liter with 2 liters filled in one of them. So let's say this one is filled with 2 liters. Or you reach some state like 10-liter, 4-liter, 7-liter, but some other one is filled with 2 liters. So this guy is filled with 2 liters. You don't care which one is filled. Just one of them should be filled by 2 liters. Okay. And what do I mean by minimum steps here? I mean, so this costs 1 step. Filling from the tap like costs you 1 step. 1 step can be treated as like 1 minute. And pour operation also costs you 1 step. No matter how much quantity is being poured, we just say it's 1 step. And emptying a jug also costs you 1 step. So in this case, think about what will be the answer for 2 liters. How many steps will you take? You can first fill in the 10-liter one, right? But then what will you do? Like just try to think of it like a math problem. Brijesh says 1. Kiran says 2. How will you make it in 2? I don't see. Like what are the steps? In the first step, what will you do? Right now there are 3 empty jugs. I think it'll be more than 2. Not sure. 5. Okay, whichever number of steps you say, just say the rough order of commands also. How will you do that? Like first you'll fill this one, then you'll transfer, whatever. I think you can do one way is that you fill in the 10 guy completely. Then you pour it in the 7 one. So 3 is left here. Sorry. You pour him in the 7 one. So this is full now. This is 3 left. Right? Now, when 3 is left here and 7 is here, just discard the 7. Not sure. Okay, this is tricky. Yeah, exactly 2 liters, Prajesh. Fill 10, pour into 4, empty 4, pour into 4. Okay, nice. Yeah, that's good. That I think can be the optimal. So, Shruti's solution is fill the 10-liter jug completely. Right, that's one operation. Now, in the second operation, you pour it into 4 guy, and this guy becomes 6. Right, and now you just discard this. So that's the third operation. Empty it out, and then this is 6 right now. Again, pour him inside this. So that's the fourth operation. And then discard it again. Or basically don't even, like, you don't like, yeah. Either way, you'll end up with 2 liter here now. Can't we pour only 2 liter in one jug directly? No, Wired. The question itself, I initially mentioned in the question that if you're filling the jug, you have to fill it completely. That's the rule of the game. So if you're filling a jug from the tap, you have to fill it completely. And if you're pouring, then you have to keep on pouring till the time either one of them becomes full to the brim or the other one gets empty. It's a very like common puzzle, like an interview puzzle or something. So, I mean, in the puzzle, you have to orally do the question, but like okay, now think about this. If instead of 10, 4, 7, I hadn't fixed the value and I put A, B, C variables, like A liters, B liter, C liter, and the target value was D liter, then this could have been a comparative programming question, right? From A to everyone, will there always be a solution? Not necessarily. Like in this case, 10, 4, 7, there, I don't know. No, there isn't always a solution. Yeah, that's for sure. I think the derivation of that comes from GCD of these 3 values, 10, 4, 7, and other constraints. Okay. Anyways, okay. Now, can people try to think of what kind of graph structure can be used to answer this question? Minimum number of steps. When we have A liter, B liter, C liter, 3 jugs, and we want to make D liter amount in one of the jugs in minimum number of steps. That's what we want. The number of steps required, minimum number of steps required. Like, how can we transform this into a graph question? Initially, you might not see the graph, that what is the graph here? Because like you're doing a water jug problem, you're transferring water from one jug to another. Okay, Heather is like, how do you think that it's not a greedy solution? Primarily because, okay, intuitively you think about this. If you have to make 2 liters and you have made 3 liters, it doesn't mean you're close to making 2 liters. If you want to make X liters, let's say 10 liters, 7 liters, and you have a very, okay, in this question, think about this. You can make 7 liters in just one step, but you can't make 8 liters in 2 steps also. For 8 liters, you'll probably require a lot of effort, right? So that's why the greedy doesn't seem right. In greedy, you generally say that if something close can be made quickly, then this thing can also be made quickly, relatively quickly. AA says to everyone that can DP work? Yes, DP can work indeed. DP will work if you do the DP correctly. But you'll realize that DP and BFS here are pretty much the same. I'll go through this once I make the graph. Okay, if people can think of the DP, then just try to explain what the DP will be. Yes, Russell is pretty much, I think Russell is spot on. Each set of volumes in all that could be a node. And when you perform one of the steps, that would be an edge. Yes. So think about this. When I was making all these drawings, you could represent these drawings in a more compact manner by saying we have a 3-element vector, like 3-element thing, basically a triplet. Initially, that triplet is 0, 0, 0. That means nothing is filled. All the 3 jugs are empty. Now, when we, let's say, fill in the 10-liter jug, we get 10, 0, 0. Now, let's say we transfer this amount to the second jug. I'm explaining Shruti's solution. Now, what it becomes is 6, 4, 0. Now, I empty out the 4 guy. So it becomes 6, 0, 0. Now, I transfer again from this to this. So it becomes 2, 4, 0. And I maybe empty out him again. So it becomes 2, 0, 0. This is a very compact representation of the given problem. You don't have to draw those jugs again and again. You can just think about it like a triplet getting modified each time by those operations, right? And these arrows denote the operation happening. So this is the first operation, this is the second operation, this is the third operation, this is the fourth operation, this is the fifth operation. This one is a fill operation, this is a transfer operation, this is a discard operation, this is a transfer, this is a transfer operation, this is a discard operation. Yeah, so Rushil has linked some Google CodeGem problem. You guys can look at it later if you want to. Yeah, it might be a nice, it should be a nice problem. I mean, if it's a Google CodeGem problem. But yeah, so now people can see that these values denote a state. In my agenda, I said internal state. But by internal state, I meant is these value. Like this triplet is basically a state of the game. That is, you have 6 liters in the 10-liter jug in the first jug, you have 4 liters in the second jug, and you have 0 liters in the third jug. That's the state of the game, right? And from that state, you can transfer, you can move to a lot of states. So let's say you're at the state 6, 4, 0. Now till which all states can you move? One state you can go to is discard the 6-liter guy. So 0, 4, 0. The second state you can go to is discard the 4 guy. So 6, 0, 0. The third state you can go is fill the 6-liter completely. So 10, 4, 0. Okay, and these are directed edges. If you can't go from 0, 4, 0 to 6, 4, 0, that's not allowed, because if you fill in this guy, you have to fill him till 10 completely. So these are directed edges. What else can you do? You can fill in this guy also. So you can go to 6, 4, and 7. Right? That's pretty much it. So from this state, you can go to 5 other states. Sorry, 4 other states. Do people get this? That when you are at a state, you can go to other states by one step. And you can represent each state as a triplet. 0, 4, 6. No, you can't do that, because this guy is actually 7-liter jug. The third jug is actually a 7-liter jug, right? And no problem. And in one operation, you can empty this guy. So you can go to 0, 4, 0. In the next operation, you can go to 0, 4, 7 if you want to. 6, 0, 4. No, I mean, why are you guys confusing the orders? Okay, I'm just saying in one step, what all can you do? Not in 2 steps or 3 steps, in one step. In one step, you can only go to these neighbors, like these guys. Just think about one step. Will 640 not direct to 640 again? Okay, you can do if you want to, but like, yeah, it's optional. 604 is transfer 4 to 7. Oh, nice. Sorry, I didn't see that. Sorry. Yeah. So yeah, that's also possible that you do transfer from 4 to this 4-liter to here. You can even do transfer this 6-liter to here. Yeah, I forgot those states. Sorry. So 0, 4, 6. What else can you transfer? You can transfer this guy to this guy. No, you can't do that. You can transfer this guy to this guy. You can transfer this guy to this guy. You can transfer. Yeah, I think now we are covered. We can transfer 6 liters from 10-liter jug to 7-liter jug. Yeah, I forgot these 2 states. Okay, and the third state which people are referring, which is also correct. You can transfer from this guy to this guy. Sorry, I forgot some states, but yeah. So, but people do get the idea pretty clearly. Yeah, it seems. So in one step, what all you can do is like those states, right? Now think about this. How many maximum states can you go to? So if you are at a state, let's say the capacities are A, B, C. The capacities. So in our example, A was 10, B was 4, C was 7. That was an example. Let's say the capacities are A, B, C. So you have a node, let's say X, Y, Z. How many different nodes can you go to? One option can be that you empty out X, right? The other option can be you empty out Y. The other option can be you empty out Z. So there is 0, Y, Z. There is X, 0, Z. There is X, Y, 0, right? All these options. So you have 3 options when you discard. Similarly, you have 3 options when you fill. That is when you say, let's fill X till A, the full capacity. So A, Y, Z, or X, B, Z, or X, Y, C. So these are fill operations. You have again 3 fills. And what about transfers? Exactly what Varshit wrote is pretty much spot on. How many transfer do you have? You have 3 elements and you have to pick 2 guys, and the first guy transfers to the second guy. So The number of ways to pick the first guy is 3, and the number of ways to pick the second guy is 2. So 3 into 2, 6. Okay, it's not 3 choose 2, it's more like 3p2, because the order matters. Node A is transferred, like jug. First jug is transferring to second jug is different from second jug is transferring to first jug. So you have 6 ways. So you have 1, 2, 3, 4, 5, 6, 6 transfers also. Right? Maybe some of them are invalid, but these are the at most number of edges that you can have. Maybe some of the transfers, some of the drops, or discards, or some of the fills are invalid, but that's the maximum you can have, right? So that's 3 plus 3 plus 6, which is 12. So you can have at most 12 outgoing states. Right? Now, think about this. How many internal states are possible, like this X, Y, Z? So the first value goes A, the second is B, the third is C. How many internal states are possible? Like all the different X, Y, Z is possible. I'm waiting in the comments. I think someone should get this. How many different states? Like this is one state, this is another state, this is another state, this is another state. How many different states can we have like this? So what I'm asking is how many different triplets can we have? Anshul was quite close. A, B, C, A into B into C. It's actually A plus 1 into B plus 1 into C plus 1. Because the first jug can have the value from 0 to A inclusive. So even the value can be 0 or A or anything in between. The second jug can have the value from 0 to B. The third jug can have the value from 0 to C. So this jug has values A plus 1 different values. This has B plus 1 different values. This one has C plus 1 different values. And you multiply all of them. Yeah, Varshit is correct. That's the maximum number of possible states, right? So in your graph, what will be the number of edges? Sorry, number of nodes. It will be A plus 1 times B plus 1 times C plus 1. And what will be your number of edges? It will be 12 times V, less than equal 12 times V. So, okay, obviously these are all loose upper bounds, correct? Everyone is correct on this, that these are not precise correct things, right? Yeah, Narendra, I'll show that too. So basically how the graph will look like is you have a 0, 0, 0, and you have some states going from it, like maybe 10, 0, 0, maybe, oh, I'm again shifting back to the example, 0, 4, 0, 0, 0, 7. And from here also you'll have some guys. You can have cycles or everything. Like everything is possible. It's not a tree really. You can have cycles. Like let's say this is a node, this is a node, this is a node, and this also goes to the same node. Like things can happen. But people get the idea of the graph, right? That the state is represented by a triplet and you can move from state to state. And the number of edges is bounded by 12 times V, because each guy had only 12 neighbors at most. Maybe they have 7 neighbors, maybe they have 8 neighbors, but they can have at most 12 neighbors. So in total, the number of edges will be 12 times the neighbors each guy has. Sorry, the number of neighbors each guy has times the number of nodes, which is 12 times V. And the number of nodes is also going to be at most this much. Now the problem reduces to a breadth first search. You're starting from 0, 0, 0, and you're trying to find what all things are reachable. And like, what's the minimum distance to reach that thing? Because you have the states defined. Had you been thinking from a DP point of view, you would have got on the same thing. Your DP dimension would be something like DP XYZ, and your movements will be very similar to how the graph movements look like how the transfers and everything look like. So if someone was thinking from the DP line, they would come to the same solution. Maybe they don't code out the solution in a graph manner, so they don't explicitly write out a breadth first search. Instead, they do a 3D or a DP, but it will be the same thing conceptually. And each node is made because it's a min of some things. What will we try to reach? Like any of the jug can have 2 liters. Okay, so Varshit, what you'll do, okay, what we will do in this algorithm is we'll start from node 0, 0, 0, run a BFS. So in a generic graph, think about it like a generic graph problem and run a BFS. And then we'll have a distance array, right? We'll have a distance array. Maybe the distance array is like XYZ, 3-dimensional array. Then what we'll do is basically, we'll say, what's the distance to node 2, 0, 0? What's the distance to node 0, 2, 0? And what's the distance to node 0, 0, 2? And just take the minimum of these. That's our answer. Do people get this? That we'll run a breadth first search on this graph from the source, which is 000, because we were given an empty state. Okay, I defined the question that way, that we want emptiness. That's why I'm asking this. Yeah, I mean, it depends on how the question is defined. If the question is like any one of the jugs has to be 2 liters and the other jugs can be anything, then you're correct. It will be more like then dp2 comma alpha beta, dp alpha 2 comma beta, and dp alpha beta comma 2, and take the min over all possible alpha comma beta, right? Constraint on number of jugs will be low in this question then. Yes, generally, I think in sort of this question, like you have only 3 or 4 jugs. Yeah. Okay, Chandramani asks, there might be multiple ways. That's why we are using a breadth first search. Like when you read the question, and like the reason why you should try to think of a breadth, like even consider a breadth first search in this kind of question, is because we are trying to minimize the number of steps, and breadth first search is like minimum distance, and steps here is distance. In this question, we defined one step as 1 unit of distance. So that's why minimum number of steps is automatically satisfied when we do a breadth first search, because a breadth first search will find the minimum number of steps. Okay, so everyone is asking, how do we generate this graph programmatically, like in the program? Like how do we implement this thing? I'll just go through the broad pseudocode. I mean, I'm not trying to implement this thing actually right now. It's generally straightforward. It's not that hard. So, okay, what you can think of is, let's say our BFS algorithm doesn't change, right? We just want to create a graph. One way of creating the graph is that 3 tuple thing, right? The other way is map things. I'll just show you. So let's do this. Okay. So you have int ABC. Let's say you take in the ABC from the user. Now what you'll do is, you'll say you have a plus 1, sorry. Yeah, less than equal a, I plus plus. And then J0, J less than equal B. Okay, and you have K0, K less than equal C. Okay. And let's say ID of this guy is what? Okay, so I'll create this thing. U is equal to get ID ijk. Okay, now generate transfers U. No, let's not do U. Okay, we had 12 transitions, right? So let's create these transitions. For this is going to be ugly slightly. Counter equals 0. Okay, actually, let's just call a function here. Generate things. Generate and call ijk. And then I'll put the main code inside the generate function. That way it will be more readable, I think. Int x, int y, int z. Okay. And now what will you do? You'll say, so what I'm trying to do is, first I'll say get the ID of this guy, the current guy ID. So get ID of XYZ. Okay. And then I'll say, I'm thinking of a smarter way to do these things. F1 fill1 is equal to get ID AYZ. F2 is equal to get ID XBZ. I mean, I'm just writing out like the super ugly code which has a lot of hard coding in it. You can factorize this if you want to. Get ID 0YZ. x0c. Okay, what is get ID? People are asking. I'll just explain. So basically, the get ID is getting an integer out of the thing. Int int x, y, z. How will I get an integer? I'll say return x into plus y into c plus 1 plus z. This is like slightly tricky to get hang of, but the idea is if we get a triplet of 0, 0, 0, we want to say that its ID is 0. If we get a triplet of 0, 0, 5, we want to say its ID is 5. If we get a triplet of 0, 1, 0, we want to say its ID is c plus 1. Do you get this idea of like base conversion? It's kind of like the base conversion idea that you have a triplet and you want to map it to an integer, a single integer. Yeah, basically making a hash of every state and ensuring that like two different states always map to two different hashes. Ensuring that. So like this is a math problem, so you can just create the hash function like by thinking out the way that you can multiply this thing with the base being b plus 1 times c plus 1 and the next thing's base being c plus 1 and the next thing being c. So that's how you count, right? I mean, if this is 0, 0, 1, I count it as 1 and so on. And if it's 0, 0, c, I count it as c plus 1, sorry, c. And then this comes. And then if it's 0, 1, 1, I count it as c plus 2. What if two jugs have same base? Then also this will work. Just think about it. If b equals c, then also this will work. Because this will become out c and then yeah, things will happen. Varshit, you're correct. You can make a graph of the tuples. It's just that coding out that thing will be ugly. I think so. Like make like for most questions, you want to keep it simple and not go to the third dimension. Actually, also, yeah, that's the thing. Otherwise, I think you can make a graph on like the 3 dimensions also if you want to, and don't do the hash mapping. Didn't understand get ID. So the get ID idea is that each state can be hashed or mapped to a simple integer. I'm mapping each state to an integer. Okay, yeah, ABC was the max constraint on the jugs. Sorry, I put them in local, but like, yeah, we assume we get them in the input. The idea of the get ID was just mapping things, which was like you are given a triplet and I'm going to map that triplet to a single value. You don't even need to decode them. You don't need to decode them, but yes, the idea is that instead of keeping the tuple inside the adjacency list and everything, we are going to keep these IDs. That each state has a different ID. We'll ensure that. And I'm ensuring that using this math formula. That basically each state can be thought of as like counting. So 000 is 0, 001 is 1, 005 is 5, 00C is C. But then obviously this state is not possible. Not possible. Because the third jug has a constraint on C. Like it can't be bigger than C. So this was never reachable. So when you get 0, 1, 0, you just say it's C plus 1. Hoping multiplication doesn't overflow. Okay, we are assuming that A, B, C are less than equal to 50. So multiplication doesn't overflow. How to think or come up with this kind of hash function? Okay, so the idea was that you can think of it like a mathematical base problem. That you have 3 dashes. The first dash can go from 0 to A plus 1. Right? The second dash can go from 0 to B plus 1. And the third dash can go from 0 to C. Oh, sorry, 0 to B, 0 to C. Yeah. Anyways, what that means is the first value can have A plus 1 distinct values. The second value can have B plus 1 distinct values. The third value can have C plus 1 distinct values. And that's how we come up with the hash function. That basically, if we set 1 here and then 0 and 0, this should map to B plus 1 times C plus 1. So that it doesn't collide with the previous guys. Do you get this? I don't want to collide with the previous guys, so I want to make it at least this much big. Yeah, at the end, I can just compare the hashes of the 3 possible resultant states and get them in. That's correct. So I got discard here. And then I make the third discard also, which is XY0. And then we'll make the transfers, which is like the transfer ID, which is like 0 to. I mean, you can write them manually also. That's going to be pretty ugly, but like, I think the idea is. Yeah, you can write out the transfers also. I mean, just iterate over them. It's going to be super ugly because like the idea is you have two conditions. One is x is greater equal y. So when x is greater equal y, here you will get x minus y. Lah, I don't even want to do this actually. This is going to get like super annoying. Okay, maybe we can write it like this. Get ID. Okay, let's try to figure this out. Transfer. Let's try to see this. So you can have something like I'm thinking, what's the best way to do this? Basically, the idea is you need to have a function like transfer, which returns the pair intent k equal transfer from x to y. Yeah, something like this. And then you do k dot first, k dot second, z. Otherwise, you say k equal transfer from x to z. And you say k dot first, y, k dot second. Something of this sort. Yeah, but like it's going to get super ugly. Like I will do something like x comma y comma b. Basically tell them that x's max capacity is a. Okay, you don't need to tell them x capacity, but you need to tell them y's capacity. How much can y actually be filled? And here you need to tell them z's capacity. And then you need to do it a lot of times. I'm not going to write it completely, but like, I just showed so that people know how to do the generation. You can obviously refactor this to look very pretty in terms of loops and everything. The next can be maybe from y to z, c. And then t3 equal get id, x, k dot first, k dot second. And now I'll just show you how the transfer function will roughly look like. Maybe I might get some of the conditions wrong, but yeah. So the t function will have left jug capacity, which is like, let's say the capacity is known as R and the next capacity is known as S and his capacity is cap, right? Now you say, okay, now you say how much thing are left remaining is equal to cap minus S, right? If R is greater than remaining, then you return R minus remaining, comma cap. That is the thing gets full entirely. The right jug gets filled entirely and the left jug gets killed by the remaining amount. Otherwise, you say you return R is less basically. So R gets completely killed and you return S plus R. Right? So the remaining function, what it is meant to do is transfer R liters from one jug to another jug having S liters already inside it, which has capacity equal cap. This is what the function does. And it basically returns the pair of the two guys after the transfer has taken place. So the transfer can has two cases. Either the first jug gets empty and the second jug is still not full, or the first jug has, like the second jug gets full and the first jug still have some things left inside it. That's what I'm doing here, the if else. You don't need to care about the if else condition. That's just the idea of how to transfer. You can code out the transfer thing. And I wrote it till T3. You can keep on doing this till like T6. And once you have all of them, you can just push them inside. Like you can just say adjacency u dot pushback F1, adjacency u dot pushback F2, and so on. All the way till T, like dot dot, adjacency u dot pushback T6. Right? Do people get this now? So once you've created this adjacency list, you can just run the BFS, and then after the BFS, you can check int answer equal, let's say int max, and then you say, I don't know, or just do min over distance get ID 2,0,0, min over distance get ID 0,2,0, distance get ID 0,0. So it's actually not that hard to implement once you've like written all the generations correctly, and you have some get ID function and some transfer also, right? And I mean, these functions are in itself pretty small. The get ID is like a one-liner, and the transfer is also like a four-liner. So yeah, that's pretty much. So in these kind of questions, you have to keep in mind that it's not immediately obvious that you have a graph in the question, but you can create a graph if you think hard enough, and you try to think about the properties. Like firstly, there was a concept of states, that each thing has a state. Like the triplet was the state. So the triplet in that question was the state, and the number of steps, like step was equal to edge in the graph, right? And these things, like we just observed that number of states plus number of transitions was like almost something like, I don't know, 50 cube plus 12 times 50 cube at most. Let's say A, B, and C all are less than 50, then they're roughly less than 13 times 50 cube, right? And okay, we won't go through dig jump. I mean, I think the what is the problem is enough. Okay, I mean, you guys can say. So I think we started the session at 2:30, and we are like 1 hour 30 minutes into the session. What do you guys want to do now? Either we can go through dig jump, or we can try to go through Dijkstra, like some techniques of Dijkstra. Maybe up till the second shortest path, I guess. Probably not after that. Like, yeah. We have a very equitable distribution of votes. Okay, looks like Dijkstra is winning. No, a 1% putting it many times doesn't count, Sanjay. Okay, we'll go with Dijkstra. I think people are more interested in Dijkstra. So, just like a rough show of hands of people who understand basic Dijkstra or not. Like, if you don't understand basic Dijkstra, then we'll have to go through some of the basics. Otherwise, we can assume that you know how Dijkstra works, but how? Okay, basically in comparative programming, like at least in good contests, nobody generally tests on the very basic question of Dijkstra, because that question, yeah, once you know the algorithm, those questions are pretty straightforward. Okay, I think we need to go from basics. So let's go. Okay, then I think we'll only be able to cover till this portion. Multi-destination and multi-source with the basic. So let's remove this, and let's remove that also. And I'm not sure if CodeChef is here or not. Isn't it feedback? So, okay, I'll switch on to my iPad now. So Dijkstra is like, okay, BFS, the difference from Dijkstra is that now it's a weighted graph. So we can even take the previous example if you want to. Let's say we have a node 1 and we have a few nodes connected to it, node 2, node 3, node 4, node 5, node 6, node 7. And let's see the edges of this. And you have weights also, like how much time does it take to travel on that edge. So let's say this guy takes 7 minutes, this guy takes 5 minutes, this guy takes 4 minutes, this guy takes 1 minute, this guy takes 1 minute, this guy takes 30 minutes, this guy takes 10 minutes. Now what you want to find is give me a moment. Yep. So what we want to find is that how much time or how much distance is there for the minimum, like for each node minimum, right? So from node 1 to node 2, what's the shortest path? 7 distance units, right? 7 units. So we put 7 here. I'm not explaining the algorithm, I'm just explaining what we're trying to do. For node 3, what's the shortest path? 5. From node 1. For node 4, what's the shortest path? So there are 2 paths. Now they're actually different. In breadth first search, you could just say pick any. You don't care because each of one weight. But now the path from 2 is actually smaller. So it's 8. And for node 7, what's the shortest path? 38. For node 5, what's the shortest path? 8. For node 6, what's the shortest path? 18. Right? Now, even adding some unintuitive edges can actually shorten your path. For example, let's say there was an edge from node 6 to node 7. Okay, with the edge weight 2. Then what would have been the shortest path for node 7? 20, correct? So like maybe visually this path looks longer, but don't care because this edge is like super big, super heavy. You don't want to take that. Okay. Now, like coming up with Dijkstra on your own is like super hard. Like I don't think anyone can invent Dijkstra like for comparative programming, or like a high school or a college student can invent Dijkstra on their own. So we'll just go through the algorithm. So in the algorithm, what happens is you have node 1. Okay. Similar to BFS, you see its neighbors. So you see node 2 and node 3. Okay. And instead of a queue here, you have a PQ. By PQ, I mean a priority queue. Now, people who don't know priority queue, it's basically what all things that like similar to a queue that you can push in stuff inside the priority queue. So what you can do in priority queue is you can push stuff, you can pop min, and you can get min. Like just think about it like this API, which allows you to push in elements to get the minimum element and to pop out the minimum element. And each thing works fast. So every operation is login. So instead of the classic queue, now we have a priority queue. That's a big difference. And that's the main difference from Dijkstra and BFS. Like that's one of the main differences. Okay. So when you're at node 1 and you iterate on their edges in any order. So let's say so node 1 is in the priority queue. Okay. And it's not really node 1. It's more like the distance of node 1 comma node 1. So 0 comma 1, because that's the distance of node 1. That's the default value, 0. So 0 comma 1 is there. Now you see, oh, I have 2 edges. One to node 2, the other one to node 3. I push in both the guys in. So I push in and I pop this guy also because he's processed now. So I push in 7 comma 2 and I push in 5 comma 3. Now I say get the minimum. Now what will I get when I do get min? I call get min on this priority. What will I get? 5 comma 3, correct? Because 5 is smaller than 7. So in Dijkstra, what you do is basically when you have explored a node, right? We explored this node already and we saw 3. Now when and 2, we'll go to that guy first who is nearer to the source. So 3 is actually nearer. So we'll process this guy first. We'll say that we want to process this guy first. We don't want to process 2 first. The reason being, had you processed 2 first, you might have messed things up. Yeah. So let's process 3. Like might have messed things up as you might have got bigger answers for places. Let's say this thing was something like, I don't know. Yeah, this example doesn't really show that, but okay, let's go forward. So you see 3. Now from 3, which all nodes do you see? You see node 4 and you see, okay, you don't see anything else. So basically you can't go back because this is already explored. Okay, these are not directed edges, treat them as undirected edges. That is, you can go in any way, bidirectional, undirectional, whatever. Now from 3, you can go back, but that guy is already explored, so you don't want to. You know that you'll get something bad. Yes, it is greedy. Yeah. So now you say, okay, let's see other things that I can go to. I can go to 4. So update the answer to 4. Right now, the distance till 4 was infinity. Like from source, you couldn't go to 4 because you never knew how much distance there was. But now you can say, okay, I can come to 4 with weight 5 plus 4 because distance till node 3 is 5. So distance till node 4 is 5 plus 4, 9, 9 comma 4, right? You can come with 9 weight to 4, node 4. So you push in 9 comma 4 in your data structure. Now, the difference from BFS is it's not guaranteed right now that this is the best distance for node 4. It's not guaranteed. Now so in Dijkstra, the time when it gets guaranteed that you have found the best distance is the time that thing is processed, not the time when it's pushed. There is a difference between getting pushed and getting processed. Getting pushed is more like when did you get inserted in the data structure? That's not important. Like that's not when your value is fixed. Your value is fixed when you're processed. Example, when we saw the get min and we found out 5,3, we decided now we will process 5,3. So at that time, we can guarantee that this node 3 has the minimum distance of 5 and it won't ever be updated. This can't get smaller than that. So this guy is fixed. Like this value is fixed. The 5 value is fixed. That's a very subtle difference from BFS, but that's an important difference. Now, after putting in, okay, now we pop out 5,3. Now, what will be the get min? What will get min give us? Will it give us 9,4 or will it give us 7,2? It'll give us 7,2, right? So we'll be at 7,2 and we'll see its neighbors. So it has neighbor to 5 with 1 weight and to 4 with 1 weight and back to 1 also. It won't go definitely back because that's already processed. It can go to 4 also still because that guy is not processed. It has been pushed, but it hasn't been processed. So he can go to 4 and he will go to 4. And okay, now when he goes to 4, he'll ask the question, can I improve 4 or not? By improve, it means can the distance to 4 become minimum because of me? Can I minimize them more? If I can, then I should. So what's the distance till 4 he contributes? 7 plus 1, 8. And what's the current distance to 4? 9. So he can minimize it. So he will minimize it. He'll put 8,4 here. And you will change this 9 to 8 in the data structure. Do people get this? Because he could minimize it. That's why he did that. Like, had it been the other way around, had it been that this is right now 9,4, but this edge weight is like 6. And here it's 9,4 present. Okay, then it would be 7 plus 6, 13. 13,4 is actually pretty big. So you can't do that. You can't do that change. Like 13 is bigger than 9, so you won't do that change. You'll just let it be. Okay, Rushal asked a very good question. How can you change things in a priority queue? You don't have that operation, right? He's correct. We don't have that operation. So what we actually end up doing in priority queue is, now this is like not what the original guy, the Dijkstra guy, did in his algorithm, but this is what most people in comparative do. When you see 7 plus 1, 8, you push in another copy of 4, 8,4. So now when you see that I can improve the distance, I push in another copy. This is different from breadth first search, in which we guaranteed that in the data structure, we only push one thing once. Here, you can actually push one thing multiple times. So basically, Dijkstra has 2 versions. One is the heap version, in which you won't do that, in which you will push only once. And then you can modify things, but you won't push them again. And the other is priority queue version, in which you push multiple times also. This one is more popular in comparative. Popular. If implemented incorrectly, this can be slightly slower also. If incorrect, slower. Oh, sorry, my bad. Yeah, someone is correct. Priority queue isn't only heap, right? Yeah. Sorry, this is balanced binary search tree. This is like balanced binary search tree or a smart heap. I won't explain what a smart heap is, but Just ignore it. Okay, don't ignore the smart thing. Yeah, just think about like a balanced binary search tree, like a set. If you use a std set, C++ set, then you could do that push only once and you could do the modifiers. Yes, JD, it will lead to more space requirements, but if you implement it correctly, you can still have the space in V plus C. You won't take V square or EV or something like space. You'll still take V plus C if you implement it correctly. That's one of the things when you do priority queue, you have to take in mind that your implementation should be quite correct. So after 9,4, you inserted 8,4 also. And you won't, okay, you'll insert this guy also, right? So you'll insert what? 5, 8,5. 7 plus 1, 8,5. Right? And right now this distance is fixed. Node 2, for node 2, you can't get anything better than node distance 7. Now you pop node 2 also. Now you again see who is the min guy in my heap. Sorry, in my priority queue. What is it? It's, let's say it's 8,4. I mean 8,4 and 8,5 are technically a tie because both are the same distance. Pick any of them, doesn't matter. Let's pick 8,4. When we pick 8,4, now we see what are the neighbors of 8,4. It has a neighbor 7, node 30, 30, and some other neighbors also. This guy is explored already. We don't go here. With this, we don't go here. These are processed. This guy is not processed. We go there. Okay, because we got it as a min, now we know that the answer is definitely 8,4. That is, there is no other way to get to 4 with a better answer. You can't get to 4 with a better answer. Like you can't get to 4 with a distance of 7 anyhow. Okay, so from 8, what you'll do is, sorry, from 4 you'll ask 7 and you'll get what? 30 plus 8, 38, 7. So you'll push 38, 7 in your data structure. And then what will you do? Nothing else. So you'll pop him out. Now you have 8,5 in your heap, the get min, right? So you'll see min 8,5. You'll ask him to go to 6, and the distance is 10. And because you popped him, that's his answer fixed. That is the best value that he has is 8. That's done now. And 8,5, now this becomes 18. Sorry, not here. You insert in your data structure 18,6. Right? That's the distance till node 6. Now an interesting thing happens. You pop this out. What will be the next min in your data structure? 9,4. But you notice that 4 is already processed. So you don't do anything. You don't even go through these 3 guys. You don't do anything. You just skip him. You just see that he's present. He's there in my priority queue. But I already know that he's processed, so I don't need to process him again. So I just pop him. That's how you save time. In my BFS code, I wasn't saving time like this. Had I coded it that way, then I could have saved time. That whenever I see element the second time, I just continue. I don't care about it. I just pop him out and don't do any processing. If I do that correctly, then I can, like, my implementation won't be buggy. Won't be slow. Now after this, what will you see? You'll see there's 38,7 and there is 18,6. Which one will you take from the get min? Yeah, Manthan, I'll add the session for today. The code later on. 18,6 you'll see. So 18 is fixed now. And he can go to 5, but obviously 5 is already processed, so no point going. And 7 is not processed, so you can go to 7. And the distance to 7 is actually 2. So he can actually improve the distance for 7. Earlier it was 38, now he can make it 20. So he'll put in 20 also. So he'll put in 20,7 in the data structure. And you'll pop this out. Now you'll see 20,7 in the data structure. That means the distance is fixed for 7 to 20. And you'll pop him out. Because nothing can be processed because these guys are processed already. And yeah, this value is just discarded because the value is already fixed. I hope everyone got the broad idea of the Dijkstra. You have a data structure, priority queue or something. You take the min again and again. You process the unprocessed guys, not the unvisited guys, the unprocessed guys. Sorry, the unprocessed guys. And for each of them, you see, can I improve him or not? If I can improve him, then I should improve him. And you put the improved copy inside the data structure. I won't go through the proof, Manan. You can look at CLRS, Corman book, the big fat book, or you can look in Comparative Programming 3, or you can look in Wikipedia article, or like some top coder article. Basically, there are a lot of internet proofs present for like why this works. The way you should think about it is intuitively that when you see a node and it's processed, try to prove that now it's guaranteed that this node has the correct value. That is, this node's value can't be changed in future, which breaks if we have negative edges. So if you have negative edges, okay, Sanjay, Dijkstra doesn't work sometimes in case of negative edges and cycle converting negative edge forwards and which can explain this also. If I do CSE, is it enough for AMI? If I do CSES, I don't know what is CSES. Yeah, for Sanjay's question. If the water problem was instead of minimum steps, you need to print out the minimum water thrown out, we could use Dijkstra, right? Yes, you could. Yeah. I mean, so everyone just please put all the questions on the everyone, because right now I'm on iPad, I'm sharing my screen. So other people can't see chat through my screen. So you should put your question on the everyone. So that people at least know what I'm discussing. So this Vivek question is pretty good, that if the previous problem has a variant, say, or like we want to minimize the amount of water wasted and something like that, then we could use it extra, because we could just say that whenever we do the discard operation, that discard operation is weighted. That is, it actually has a weight, that edge has a weight. That is, if we are wasting 7 liters, then put 7 there or something. And then we could say, like, maybe take more steps, but do minimum number of discarding. Yeah. CSES, I'm not sure, Baxi, what is it? I mean, I think it's some European contest, but I'm not sure. Manan asked for proof. I said proof is available online, but we're not going to go through it. Sanjay asked for negative cycles. Yeah. So in the negative cycle thing, okay, that's a good question actually. Okay, in general, don't do Dijkstra for negative cycles. That's the thumb rule. But why it doesn't work is because, let's think about this. So let me think. Okay, in this graph, let's say this, I'll slightly modify this graph, okay? All the edge weights are previous, the same guys, but there's a new node, node 5. Okay. Yeah. So I added one more node inside, node 5. From node 1, the edge to node 5 is 20. From node 5, the edge to node 4 is minus 15, negative edge. Now, what will happen? Something cool will happen. So from node 1, you'll see what will you push in your queue. You'll push 5, 3. You'll push 7, 2, and you'll push 20, 5. Right? All these three things get in your data structure, and this thing gets popped out. Now, what will be the next thing? 5, 3. So you'll pop him out, and you'll push 9, 4. Right? 5 plus 4, 9, 4. Now, what will you see? You'll see 7, 2. So you'll pop him out, and you'll push 8, 4. Now, what will you see? You'll see 8, 4. Right? And maybe there is some big graph here, G. Okay. Now, when you see 8, 4, you'll do some processing and put in some other things, blah, blah, blah. When you process 8, 4, you're kind of guaranteeing that, okay, 8, 4 is the final answer. Okay, let's say there is another guy here. Let's say node 6 is here, and this edge is node 1, weight 1. So when you see 8, 4, what you'll do is you'll see 8, 4, okay, and then you'll update node 6 and put 9, 6. Right? And you'll pop out 8, 4. When you see 9, 4, you'll just pop him out because 4 is already processed. Now, when you see 20, 5, things break, because when you see 20, sorry, you'll see 9, 6 next time, and you'll do nothing because you can't go back and things like those. Now, when you see 20, 5, things break. Why? Because when you see 20, 5, you'll see here 20, and you'll see his neighbors. Node 1 is already explored, so ignore that. Node 4, I can get a better distance to node 4 by mistake now. So I can actually get a better distance to node 4. So maybe I update it also correctly. Maybe I say, okay, make him 5, 4. But even if I do that, I won't be able to update node 6 correctly. Whereas node 6 also technically now has a shorter path. So that's how things break. So there are two versions. One version is that you just you give wrong answer on negative cycles. The other version is you get TLE on negative cycle, on negative edges, not cycles, negative edges. One version is where you get wrong answer. In this version, you get wrong answer. The other version is you get 5, 4 here, and you push 5, 4 inside your data structure. When you push it, you'll gradually make the 6, 6. But in this case, you'll get a time limit exceeded. So do people understand why negative cycles won't work? You can implement it in two different ways, but both the ways are bad. None of the ways can get you accepted. One way is don't process when you see 5, 4 afterwards. So just put 5, 4 here. In that way, you get a wrong answer because node 6 now knows incorrect value. It thinks that the shortest distance from node 1 to node 6 is 9, but it's actually 6. Take this, take this, take this. You know the incorrect value, so wrong answer. What if we updated correctly? That is when we saw this thing, we actually put in a 5,4 in our data structure. Then we could have updated this also to 6,6, but this will explode in time limit. I won't explain why this will explode. You can just think of a case. Like in BFS, I gave you this case, right? 1, 2, 3, ... and all of them going to n. Something like similar will work to show that it will TLE. The complexity will become something like V square. So for negative edges, use Bellman-Ford. We are not covering that right now in this class, but like you can read it up on the internet or something, but use Bellman-Ford. That's another algorithm that works correctly for negative edges. And if there is a negative cycle, what we mean by negative cycle is, let's say there is a node A, goes to node B, goes to node C, goes back to node A. And let's say this weight is 10, this is -7, this is -5. Now what you can do is you can just keep on going through the loop and collect -2s. So when you go through once, you get a -2, right? 10, -7, -3, -5, -2. You keep on collecting -2s, keep on going through this loop infinitely, and you can make the value as small as you want. You can go to negative infinity. So if you have a negative cycle in your graph and say you are at this node, you go to this node, go through the negative cycle a bunch of times, and once you have negative infinity, go to the destination. So technically the question becomes invalid then. Like, what are you trying to ask? So the question generally is there a negative cycle in the graph or not? What we mean by negative cycle is the net sum of the cycle is negative. Not that all the edges are negative. Maybe all the edges are not negative. In this case, one of the edges was actually positive in the cycle. This guy was 10. But the total sum of the cycle was negative. So you could keep on going through it infinite times. So if there is a negative cycle, Bellman-Ford can detect it. It will be able to answer, yes, there is a negative cycle. Dijkstra can't detect it. And if there is no negative cycle but still negative edges, then Bellman-Ford can give the correct answer. So Dijkstra in general doesn't work with negative edges or negative cycles. And Bellman-Ford works with negative edges and detects negative cycles. Obviously, nobody can work with negative cycles because then the answer is just minus infinity. For a lot of cases, not for every case, but yeah. So, is Dijkstra cool with people? I mean, I sidetracked here a bit for the Bellman-Ford portion, but like the Dijkstra portion, that is, you have a priority queue, you're doing stuff on it, and yeah, similar to BFS, somewhat. But just the difference is that there's a priority queue and you have some different processing rules. Cool. So let's just go through the drawing part first. I'll go through implementation later, but like, so in this question, what we were doing is we had a single source, which was node 1. And we were saying, get the answer to all the other guys. So this was multi-destination single source. That is, our source was only one node from which we were trying to get, but the destination were a lot. Now let's change the question slightly. Think about this version. There is a city. So there are some cities connected via roads. Okay. And like the roads have like some distances, kilometers on it. And the question is this: you have a thief on a node. So let's say the thief is here, and you have a bunch of cops, policemen. Okay, so you have a cop here, and say a cop here. So you have 3 cops: cop 1, cop 2, cop 3. Now all of them are trying to catch the thief. Okay, the thief just stays here. He's pretty dumb, so he just stays here. Okay, what's the fastest way to get to the thief? That's the question. So you have many sources and a single destination. What will you do? One way is you run a Dijkstra from cop 1, try to find what's the shortest path till thief. Then run another Dijkstra from cop 2, try to find the shortest path to this guy. And the third is cop 3, find the shortest path to the thief. Then you require 3 Dijkstras. And in general, if you had like k cops, like C1, C2, C3, ... CK, k cops, then you would have required k Dijkstras. Can you do better than that? So someone answered, yeah, make this thief the source. That's correct. If you make the thief the source, what one thing do you have to be careful about? Yes, reverse the direction of edges. So now you'll have to reverse the direction of edges. So let's say original edges were like this. Now you'll actually say, oh, let's assume there's a fake edge from here to here. And let's say there's a fake edge from here to here. And that's equivalent to saying that cop1 can go to thief is equivalent to saying thief can go to cop1 on the reversed graph. So now on the reversed graph, we only need to run Dijkstra once. Do we will get this? On the reverse graph, we only need to run Dijkstra once. So this is one of the techniques that people like. Whenever you see comparative programming Dijkstra questions, generally speaking, nobody will ask you directly, do a Dijkstra on this graph. That's too simple. Like if you know the algorithm, you can just implement it and you're done. So people generally ask some variant like this. Like this is one of the variants. Okay, why are we reversing? Okay, so we are reversing because let's say there's a path from cop1 to thief. Okay, it goes through 2 nodes. Now in the reverse graph, when you run Dijkstra from thief, you can't go to cop1 on these edges. You actually need to reverse them because you're not running the Dijkstra from cop1, but instead you're running the Dijkstra from thief. Had it been undirected, yes, you could keep it undirected, because undirected means there is an edge like this, which on reversal also looks like this, right? This edge is basically equal to this plus this, and on reversal also it will look like this plus this. So it's the same thing. So if it's undirected, you don't care, but if it's directed, you have to reverse edges. But why? Okay. So do you understand the slow method, Purnima? That you have a cop1, you have a cop2, and you have a bunch of other cops, and you want to find the minimum distance to thief. So what you do is you run a Dijkstra from this guy, you run a Dijkstra from this guy, like from cop1, from cop2, from copk, and say for each of them, what's the minimum distance to get to thief, and whoever can reach him faster that's the answer. But that required you a lot of Dijkstras. That required you k Dijkstras. But we want to do it in one Dijkstra. So to do it in one Dijkstra, we say, okay, let's make the thief the source actually, because everyone wants to reach the thief. So let's make thief the source. And from thief, run a Dijkstra to the cops. But let's say there's a path from this cop to this thief. Now, when you run a Dijkstra from the thief, can you use this path? No, you can't. That's why you need to reverse these edges. Because the way of traveling is still correctly defined if you reverse the edges. If you reverse the edges and you go on this path, then in the actual problem, it means there was an actual original path. The two problems are like the same, just that this one works on the different source. That's why you need to reverse. Otherwise, you can't reach from cop1 to thief. Okay, understood. Good. Okay, now let's think about the variant, another variant. So now, in this version, you have a bunch of cops and you have a bunch of thieves also. So you have T1, T2, ... TM. And there's a graph, inherent graph, like some whatever graph. What do you want to find is fastest way to reach T1, fastest way, or whatever, fastest time to reach T1, to reach T2, and so on for every TM. So for each thief, I want to find what's the fastest way. Maybe cop1 can reach thief1 very fast and thief5 very fast. And maybe cop2 can reach thief2 very fast, like the fastest among all the cops, and thiefm very fast, or so on. Now, how many Dijkstra calls do you require? Yep, so Sanjay, I think knew the answer, but like, yeah, that's pretty cool. So the question is, for each thief, we want to know, Ashish, for each thief, we want to know what's the fastest way to reach that thief from any of the cops. So maybe like the closest cop to thief1 is cop2. The closest cop to thief2 is cop3, and so on. And what are those distances we want to find? So one way can be for each cop, you try to find the distance, like run a Dijkstra for each cop and combine the answers. So that's k Dijkstras. The other way is on the reversed graph, run a Dijkstra from each thief. So that's m Dijkstras. So I think we all agree that there are two ways in which one way is k Dijkstras, the other way is m Dijkstras. Is it like one thief can only go to one cop? No. One cop can go to multiple thieves. That's allowed. Yeah, that's exactly what A is saying is correct. Like for each thief, find the minimum of cop comma thief, distance from cop to thief for all cops. Yes, a single cop can catch two thieves. That's allowed. Although that's not realistically possible, but in this question, it's allowed. So it's not a matching question. Don't think of it like a matching question. A single cop can go to multiple thieves. So how many Dijkstras can you do it? You can, I mean, if you think about it hard enough, you can do it in K or M Dijkstras, but you can even do it in one Dijkstra. Yes. So now in multi-source, multi-destination, you need a common source. So what you do is you create a dummy node, or basically say the way you think about it is that all the cops are connected to say a central cop unit or something, maybe basically the idea is they're all connected to this god dummy node. Okay. All the cops with weight 0. So the idea is from any cop to any cop, the distance is 0 because this dummy node exists. Okay. And now all the thieves still exist normally. Blah, blah. And now you say from this dummy node, try to do it extra. So how it will look is, I'll create the graph more beautifully now. This is the dummy node. Call it dummy source. It's connected to cop 1, cop 2, cop K. Okay. And you have the graph structure here, G. I'm not going to draw the graph structure. There's a thief 1 here, there's a thief 2 here, there's dot, 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 there's a thief M here. What we are saying is run a Dijkstra from this dummy source. The idea is that let's say the shortest path from dummy source to cop 4 is through cop 1. So cop 1, then you go to one node, then you go to cop 4, thief 4. And let's say this path is pretty fast. Then you know that, okay, there is no better way to reach thief 4. Had the better way been through cop 2, let's say cop 2 also had a path to thief 4, some like through some nodes. That path is definitely worse because our Dijkstra took this path and these edges are 0 weight. So technically the path from cop 1 to thief 4 was better than the path from cop 2 to thief 4. That's why Dijkstra picked this path to go to thief 4. Understood? Okay, Mayank, what you're explaining will be slightly confusing, but that will also work. That we connect all the thieves to a single node, but we then have to work on a reverse graph. You just have to keep that in mind. If you connect all the thieves to a single node dummy destination, not dummy destination, more like reversed dummy source, and you work on the reversed graph. I won't explain that. That's unnecessarily confusing, but that will also work. Shruti, we could use this last time also, right? Yes, you could use this last time. But last time the other thing also worked. Now the other thing doesn't work. Just reversing this graph is not enough because you have two sets. There is a source set and there is a destination set. So just reversing the graph doesn't work now. Yes, it did work earlier because that time. So the idea is there are three versions. There are four versions. One version is one source, one destination. That's the simplest version in Dijkstra. The other is one source, many destination. The other one is many source, many destination. Sorry, many source, one destination. And the last is many source, many destination. What I want to explain why this variance is that all of them are possible in one Dijkstra. This is different from all pure shortest path. When I mean many source, many destination, I'm saying any of the source can reach any of the destination. Not specific source to specific destination. More like whichever source is closest. So cop thief question is a pretty good example of that. But all of them can be done in one Dijkstra. The one source, one destination, and one source, many destination are trivial, just run a Dijkstra from that source. When you have many source, one destination, either have dummy node for the source or reverse graph, reverse plus Dijkstra from destination. And in the many source, many destination, the only method is using dummy nodes. Everyone gets this? Will the complexity depend on choosing where should we add dummy source for either cops or thieves? Not really, because anyways, it's going to take one Dijkstra. And the number of edges or the number of new nodes you're adding is negligible. You're adding just one node. So the number of edges you're adding is only at most order V, because you have at most V nodes as cops. So the new graph with the dummy node is going to be pretty small, like still similar to what it was previously in terms of number of edges and number of vertices. So it doesn't matter. Can you explain how the biggest part, how dummy node helps? Okay. So think about this. When you create the dummy node and run the Dijkstra, let's say you get an answer to thief 4, and the answer is go, and the answer is basically take this edge, take this edge, take this edge. That means you found one path from cop 1 to thief 4. Now I'm claiming that this path is the best path to reach thief 4. That's my claim. I'm going to prove it. Think about this. If there was a better path, proof by contradiction, if there was a better path to reach thief 4, that is, there was some other cop who said, I can reach thief 4 faster. I have a better path. So let's say this path was weight 20, and there is another cop who's saying my weight to thief 4 was actually only 17. Then our Dijkstra actually ran incorrectly, because he should have found this way, because he was connected to that cop. He should have found that way, but he didn't. That means this 17 actually didn't exist. He's just bluffing. That thief, that cop actually couldn't reach it in 17. Had he been able to reach in 17, our Dijkstra would have found this path. That's how Dijkstra works. So basically, in the Dijkstra, when your dummy node is connected to every cop, you will find the shortest path. And also, this dummy node is not connected to arbitrary nodes. It's not connected to just generic nodes. If it's connected to generic nodes, then the issue is, let's say it's connected to this generic node, and this generic node is just adjacent to thief 4 with one weight. Then the dummy node will say, oh, I can reach thief 4 in just one cost. But that's not possible, because we know that this guy is not a cop. So going through this is not actually a valid answer. This guy should be a cop. So that's why you only connected the dummy node with the cops. You only connect him with the cops. You don't connect him with anyone else. Like, it's a two-way inequality. You only connect him with cops so that you don't get a super good answer that's not even actually possible. And you do connect him with every cop so that you at least get the best answer. And the proof by contradiction works that if the path goes through one cop, then no other cop can claim that I had a better path. Intuitively, you can even think of this like a teleporter. Like, some people try to think of it like that. I also try to think of it like that. That basically, the dummy node introduces a teleportation from any cop to any cop. That is, we are modifying the problem to say that from any city which has a cop on it, you can go to any other city which has a cop on it in zero cost. You have this magic teleporter of zero cost. So if you want to go from cop 1 to cop I, you can just go through this guy with zero cost. Generic question. Sanjay, that is set. So in a balanced binary search tree, which is a set in our STL standard template library, you can do what all priority queue does. You can get the minimum. You do just set.begin. You can erase the minimum. You just do s.erase, s.begin. You can insert elements, and you can modify things. You can do s.find and just find the thing, erase it, and add the new thing. I mean, yeah, in set, technically you'll have to erase the thing first, but you can erase anything. You can erase some middle element also. You just find it and erase it. And then you insert the modified copy. So a set lets you do all those things. Set is slightly slower. I mean, complexity wise, it's not that slow, but if you try to run it in C++, it tends to be like 3 to 5 times slower than priority queue on average. Like at least 3 to 5 times. I think people have even seen like 10 times slowness or something. Yes, there is a Fibonacci heap thing. Even I don't know it very well, but like I think the priority queue generally works on all competitive programming questions. So we did multi-source, multi-destination. Yeah, I had another question in the agenda, which was flood filling. So in the flood fill question, I'm just orally explaining all these ideas, and then I'll just show a standard implementation of Dijkstra, and then we'll end the session. So in the flood fill question, what is there? You have a 2D grid And there are some walls. Let's denote them by hashes. These are walls. Okay. And let's say there is a person here. There is only one person. Okay. And there are water floods coming out from some places. Or let's say there is a flood starting here. There is a flood starting here. There is a flood starting here. And there's a flood starting here. Now, what happens? In every second of the game or whatever of the grid, the flood spreads in 4 directions. It spreads in this direction, it spreads in this direction, it spreads in this direction, and it tries to spread in this direction, but it can't because it's a wall. And in the next second, there will be flood here, there will be flood here, there will be flood here. Flood is basically water. And then this water will try to spread in this direction, this direction, this direction. And in the next second, so on. And here also. In the first second, it will spread here, 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 here. In the first second, this will also spread here, 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 here. So in the first second, all these happen. Okay. This is the first second. I'm just trying to show what happened in the first second. Sorry. Now in the second, what happens? All of these go one step further. So this guy goes here, this guy goes here, this guy goes here. Obviously, if a cell is already flooded, it doesn't matter if it's flooded again. This guy goes here, this guy goes here, this guy goes here, so on. So basically, in each second, if there is a flood, if there is water at one node, it spreads to the 4 sides, left, right, up, down. And it keeps on happening for every flooded square. What we want to know is, when will this person drown? Like, when will this person hit flood? When will this cell get flood? At which second will this person get flood? That's the question. And obviously walls don't matter. Like when you reach a wall, you hit nothing. Okay. Now let's explain the constraints. Let's say the constraints are, let's say it's a 1000 by 1000 grid. Okay. And let's say the number of flooded cells originally given is less than equal 10 to the power 4. And person is exactly 1. And number of walls can be anything. R into C, less than equal to R into C, number of rows into number of columns. So one way is you do a BFS from all sources, which 2 people already said. That's correct. How slow is that? That is number of floods times R into C. Okay, times number of vertices plus edges, right? Times cost of BFS. Number of floods times cost of BFS. Single BFS. And what is the cost of a single BFS? That is number of vertices plus number of edges, right? And what is that? R into C plus 4 times R into C. So that is order R into C. So the total thing comes out to be order number of flood cells into R into C. In this question, that will TLE 10 to the power 4, 1000, 1000. This is R, this is C, I guess. Yeah, Ashish is correct. Single sources to multiple destinations. So you can think of it like all these initial guys are sources and they're all trying to reach this destination. And who's the fastest guy? So that obviously cops and thieves question was similar in some sense, but like I'm just trying to show you how differently can Dijkstra be modeled. Yeah, multiple cops catching one thief. So it's like multiple water guys, like floods trying to catch one person. Like sometimes if you want to see more realistic examples of this, where like the cop thief might not make sense or something, then yeah, this version is also there. This is on a 2D grid. That one was on a graph, but conceptually they are similar. I mean, you can make a dummy node also. You can do reverse Dijkstra. So you can do reverse also. You can do a Dijkstra from this guy and just try to find what's the nearest flood cell to me. Or not even a Dijkstra. You could do a BFS. Think about it. Each edge is of weight 1. Think about this. Each edge is of weight 1. To reach from one node to adjacent guy, you only cost 1 second, right? So it's an unweighted graph. Because it's an unweighted graph, you get the benefit that you don't need to use Dijkstra necessarily. You can use a breadth first search. You can do a breadth first search from the person on the reversed graph, and the reverse graph look exactly the same because they're bidirectional edges. So you can even one approach is to do a reverse BFS from this. The other approach is to make a common source from all these flood guys and run common source and say all these are one weight, and then run a BFS or a Dijkstra from source to destination, just P. You can even make them one, but if you make them 0, then you need to run Dijkstra. But if you make them 1, then you can use BFS. Yeah. Or I think you can use BFS in any case. Yeah, just don't confuse with that detail. You can use BFS in any case because it's a unweighted graph. I'm just trying to show the different variants in which you can see Dijkstra potentially. Like on a 2D grid also, it's common to see Dijkstra when you are traveling in like 4 directions or 8 directions. And yeah. So Nachiket asked, how do we implement it? Do we have to implement? And Anmol asks, do you have to implement it using adjacency matrix? So run BFS from a dummy cell which has edge to all the Fs. Yes. Okay, so people are asking about the implementation of this particular one. In this particular one way of implementing could be the similar way as to what we did in the water jug problem. That is make IDs. So each cell is X, Y, right? A cell is X, Y. And you can say that X, Y gets maps to X into R plus Y. That's the hash function, the get ID function. The other way is to make a 2D thing. In the water jug problem also, some people were suggesting that we can use a tuple, we can use a triplet everywhere. You can even use a 2D thing here. I honestly prefer the 2D thing instead of the get ID method. I can show broad pseudocode. If there is a wall around person, we don't really care. I mean, the water hits the wall. So I'll show. Okay, let's not disturb this implementation. Let's do another one. So flood.cpp, BSCP, okay. And let's say, so the grid size is small, right? It's 1000. It's just like pseudocode writing. I'm not going to make it necessarily correct, precise. Oh, sorry. I forgot to share the screen. Yep, so everyone can see the screen. It's flood.cpp. I'm starting to write the code. Okay, so let's say we get in R, C in the input, and say we get in R rows after that, and each row is a string, let's say. That's how the input will probably be defined, right? So a string in. Now what you're going to do is you will, okay, yep, you can do something like this. So you say j equals 0, jc and you say if aij equal f, okay, then I push him in the queue and I set his distance to 0. Just carefully observe what I'm coding. So if it's a flood cell, yeah, the person will never drown. So basically, initially the distance array is set to -1, right? Milindas. So set the distance array to -1, and then you can say that if the person has a distance -1 at the end also, that means he never drowned. So just print like -1 something. P, that means desti equals I, j. So we have pair int desti. Okay, so if it's a flood cell, then I'm pushing it in a BFS queue. Otherwise, I'm pushing him I'm just setting the destination. If it's a P, if it's a person, and if it's a normal cell, otherwise it's either a dot or a hash. Dot means nothing, like you can flood that place, and a hash means it's a vault. But we don't handle those cases right now. Right now we don't handle them. Now what we'll do is, again, we'll do a BFS. So we'll say if the queue is not empty, we get q dot front. Okay, and here u is what? U is a pair, x comma y, and we pop. Okay, and we do for int I equals 0 to 4, the 4 directions. Okay, we get something more also. X equal u dot first, y equal u dot second. If is valid, sorry, if just valid, x plus dxi, y plus dyi, and so this is a very common way that people code 2D grid graph questions. 2D grid graph questions. This is the common way. So you have a valid function. I mean, that's how I code, and I think a lot of people do. Like I've seen it in other people's code also. So if it's valid and it's not visited, that means dx plus dxi and y plus dy I is equal -1. Then what you do is you set dx plus dxi y plus dyi equals dxy plus 1, and you push him in. Okay, now people might be thinking, what is this dx dy happening, right? So dx dy are two hard-coded arrays. This is a very smart trick. It's this thing. Dx basically means change in x, dy means change in y, kind of like the terms originate in calculus or whatever. But do people get this idea that I'm iterating through all the 4 neighbors of the node? I add in, so what is dx0 and dy0? That is going one step to the right but not changing the y. What is the next guy? Going one step to the left but not changing the y. What is next guy? Going one step up but not changing the x. What's the next guy? Going one step down but not changing the x. Do people get dx dy? Otherwise, I won't move forward till the time people understand dx dy. Because like sometimes people get confused, like how is this? Because if you do the if condition 4 times, if you write like 4 times if condition, that will be like super ugly code, easy to make bugs. Because if you like just wrote something incorrectly or something, you have to change it at 4 places and everything. It'll be inconvenient. So this is generally the smarter way. And you pretty much have this, and then you do something like cout d dest dot first, d dest dot second, until that's pretty much it. Now just code the is valid function. So in the valid function, we got x and y, right? And we know our r and c. So return x greater equal 0 and x less than r, and y greater equal 0 and y less than c. Sorry, and axy not equal hash. That's the valid function. Basically, what were we doing is we were asking, is this cell even valid that we are actually seeing? Is this neighbor even valid? And if it is valid and it's not visited, then visit it. So we visited it here, right? And by visiting, I mean we updated the distance dxy to +1, and it was set initially -1, so that means he's unvisited. And so if he's unvisited, this condition refers to him being unvisited. If he's unvisited, we set his distance correctly here, right? Which is like the previous guy +1, and we push him. Also, we set the distances correctly for the multiple flood values, all of them here, and we mark the destination here. So we can just print out the destination here, the distance for the destination. Now the only thing left is, how are we defining the valid? So a coordinate is valid if it's within the rectangle. That means its x is greater than 0, greater equal 0, and its x is less than r. That is, we are not crossing the x axis. We are inside the bounded rectangle, and its y is also within the rectangle, and it's not a wall. That means we can go to that node. So that's how we handle the walls. You've done BFS from all F's here, right? Yes, that's a smart thing to notice. I pushed in all the guys. So it's technically, there is a implicit dummy node. I never created the dummy node in itself. I never made a dummy node and said that, oh, mark all the edge weights 111 from that guy. But by pushing here, I'm kind of saying push dummy node to F for all Fs. You get this? So I'm actually running just a single BFS. I'm still running a single BFS. The complexity is still good. It's just that instead of just pushing in one element in the BFS originally as a source, I'm putting in multiple guys. So you can still think that, okay, just assume that there is a fictitious dummy node. I didn't create it because implementation wise, it's a like unnecessary coding. So, okay, that's a generic trick. Whenever you have the dummy node concept, you don't really need to necessarily create the dummy node. You can just think, what will the dummy node do? In this case, we know that dummy node will cause all these pushes. So we can just do those pushes manually and not change the graph. By not changing the graph, the benefit that we get is that we have to write less code. Sometimes you have to create the dummy node. Sometimes the scenario is such a way that you can't just hack it away and you have to create the dummy node as another node and add those edges in. But if this is like, sometimes there is a simpler method, which is like in this case. So do people get this? So, I mean, there are two tricks here. One is this dummy node trick and how you can keep the code concise by doing a multiple pushes instead of creating the dummy node in itself. The second trick is this dx dy, which reduces some code length. I think apart from that is like, and like, okay, maybe the valid function also. Some people don't code the valid function and like have some edge cases. Like if I'm on the edge, then I only process 3 guys or something. The valid generally makes your code simpler. So if people have any doubts, then let me know. Otherwise, that was like the broad implementation of this question. Yeah. And I think we can end the session here. I'll put this code, the previous code, and my Dijkstra implementation. I didn't implement the Dijkstra here. I think it will take some time. So I think it will be better if. Sure, Ashish. So the topics I moved were how to find the second shortest path. Okay. So sometimes the question is, given U and V, find the second shortest path from U to V. The way you do it is you run a Dijkstra from U to every other node and store the answers in the array D1. So D1x denotes distance from U to X. And you run another Dijkstra from V, run another Dijkstra on reverse graph from V to every node. Store it in D2, X denoting, so store it in D2 array basically. And this one is D1 array, right? Now you can just say answer equal min over answer comma D1k plus D2k for all k. That's how the second shortest path works. I'm just explaining the question and the solution. The question is, given U and V, you had to find the second shortest path from U to V. The answer is run 2 Dijkstras, one from node U, one from node V, but on the reverse graph, keep in mind. So you get 2 distance arrays, D1 and D2, and just say, oh, sorry, there's a flaw here, my bad. D1A plus edge weight from A to B plus D to B for all edges of the form. Yeah, I had a bad bug, sorry. So you run the 2 Dijkstras, D1 Dijkstra and D2 Dijkstra, like U Dijkstra and the reverse graph V Dijkstra, and then you say pick a edge and force that edge to be a part of the path. So I pick a edge A comma B and I say this edge has to be a part. So I say from the source get to this node which is A, from node A take this edge which goes to node B, and from node B go to node B. So just add these 3 guys and take the minimum over these 3. I mean, just Google up second shortest path later on. You'll get the broad idea. Yes, if you're taking min, it will give you the second. So the idea is, yeah, you're correct. Just push them in some sort of vector. Yeah, it will give you the total min. Just push them in some sort of vector and then sort this vector and take the second guy. Something of that sort. I mean, just keep in mind these two things. Then you can probably get how the answer will work out. Split node trick, I think, is pretty big trick. Okay, I'll share content regarding the split node trick and the shortest path module also. For split node trick, I can show you one question which is very famous. Fishmonger, I think, on Spodge. Something of this name. So, yeah, I think it's this question. I'm not sure, but I think it's this question. Let me check. Yeah, it's this question. So, Fishmonger on Spodge is super famous regarding split node trick. If you read up the solution online or something, you'll figure out what the trick is. And shortest path modulo, I can share another link. Okay, I'll just put those two links on the Discuss channel. I'll put these two links, like one of them and the other one for shortest path modulo. That's pretty much it. That's the end of the session. And CodeChef team just shared the feedback form. You guys can fill it so we know what all things we can improve upon. Oh, so the question is actually not what I wrote. It's actually, so the question is actually count the number of shortest paths. Yeah, count the number of shortest paths. So basically, let's say there is a shortest path from A to B with the cost 30, but there are many paths like this. There are like 100 paths. So you have to count those number of paths, like 100. Your answer should be 100. So I'll show you, like I'll just link the implementation and everything. I have it somewhere. And then you can see why Dijkstra is actually faster than Floyd. Yeah, and I'll share the Dijkstra implementation also. So yeah, I'll share the codes that we gave here, the Dijkstra implementation, this Fisher link, and the shortest path link. Where to read graph stuff. I guess Top Coder tutorials are a good resource. The tutorials that we shared also before, I think they cover more or less everything in BFS, DFS, Dijkstra. For Dijkstra variants, I think especially you can try out a lot of contests. Example, there is a contest by IIITH CodeCraft on Codeforces. It used to happen annually, and you can look it up. They generally have good questions. Like a lot of times they have like 1 or 2 questions based on Dijkstra. And yeah, that's pretty much it. I haven't shared it yet, Purnima. I'll share it once this session ends, and like I'll update it on the CodeChef blog of this discussion, like of this video call. Yeah, this learning session. Yeah, here basically I'll add another update here, update 3 or something, and then IIITH CodeCraft. So it's a annual online event that happens, and I think the problems are on Codeforces. You can just look them up. They have plenty of good problems, and like good techniques are generally covered in those problems. Like I saw the cops and thieves question there as it is. Like the cops and thieves question is copied from there. Yeah, I think it's some past year, 3 years old or something, but yeah, they have good questions. All right, that's the end of the session. You can fill in the feedback form. So thank you guys.